When we start, Biplav, you can give permission for sharing my screen. We'll go ahead.
Yes, sir, we can start now. So, good morning, everyone. Welcome to day 2 of this joint faculty development program on designing with FPGAs Intel. Today, we have our session with introduction to time analysis. It will be taken by Padmanabham, sir. Sir, I made you the presenter.
Sure. Thank you. I will share my screen. Thank you. Able to see my screen?
Yes, sir, it is visible.
Okay, thank you. Good morning, everyone. Welcome to the day 2 of the faculty development program. The focus of today's session is on timing analysis and introduction to the Intel Quartus Prime timing analyzer. We are going to understand the conceptual understanding in the morning. We'll understand what is the concept behind timing analysis, how to apply timing constraints, what are synopsis design constraints, right? What are the different set of timing paths, all those things. And we are also going to understand about the multiple clocks handling and clock domain crossing, and also on the timing exceptions. In the afternoon, there is a hands-on lab where whatever we learned in the morning, we are going to do hands-on, and we are going to apply timing constraints for the design and ensure that the design is not having any setup or hold violations. Right, let me walk you through the objectives. Understand the Quartus Prime timing analyzer, timing analysis design flow. Apply basic and complex timing constraints to an FPGA design. Analyze and design for timing using the Intel Quartus Prime timing analyzer. Write and manipulate SDC files. So here it is called as synopsis design constraints files for analysis and controlling the Quartus compilation. Understand the need for multiple clock domains and the concept of clock domain crossing. So we are going to understand that in detail, right? And then what are the session topics that are planned? So I will just show that also to you. We are going to understand introduction to timing analysis, applying basic timing constraints and timing exceptions. That is, what is the way to constrain a pure combinational logic paths, false paths, multi-cycle paths, achieving the timing closure. And then we are also going to learn clock domain crossing. And then there will be a lab demo and hands-on sessions in detail in the afternoon. So wherever required, I will show you a quick demo, but we will have an exhaustive lab session, and then we can also do hands-on and have a good practice of applying basic and complex timing constraints to a design in the afternoon. So to give a quick recap, what we learned yesterday is like we developed Verilog HDL, we performed analysis and elaboration, then we performed functional simulation. We did synthesis and prepare and generated the programming file. And we implemented the design onto the board. So if you have the board physically, then we can connect it, number one. Number two, if you don't have the board physically, what we did is we did a LabsLAN setup where you can upload your SRAM object file and virtually and verify the output. So what is the focus for today's session is on the timing analysis. This is the section we are going to discuss in detail in today's session. Right, so let us go into the details. When we discuss about the path, there are three types of paths which you can see. One is called as the clock path. The other one is called as the data path. The third one is called as the asynchronous path. We will put a hold for asynchronous path and we will discuss in detail about this path later. Let us understand about the clock path and the data path. It means you can able to see there is a flip-flop where there is a launch flip-flop and then there is a capture flip-flop. This flip-flop is also called as the source flip-flop, and this flip-flop is called as a destination flip-flop or a capture flip-flop. Right now we can see when there is a clock path, so you can see the first flip-flop gets the clock and then the second flip-flop gets the clock. So there is a clock path, and then there is a data path where we have T clock to Q plus T combo and reaches the data pin of the second flip-flop. So we have a data path. Based on this, we have to split the circuit into different set of timing paths. That's what we need to understand in this session. So before getting into the details of that, I need to cover up some important information. When we say timing analysis is a method of analyzing, debugging, and validating the timing performance of a design. So we are going to first analyze, then we are going to debug, and then we are going to validate the timing performance of a design. So we need to understand that when we need to perform analysis, we have to find out which is the path which is having the longest delay. That is called as the critical path. Then we have to debug why that path is having the longest delay. Then we also need to apply some techniques, and then we should validate whether what we have expected, whether the design is working at that frequency or not. We have to validate it. Now, to do this timing analysis, there are two concepts. Like there are two types of timing analysis which we can do. One is called as the static timing analysis. The other one is called as the dynamic timing analysis, which is called as DTA. What we are going to do and what we are going to learn in this session, and what we are going to approach in the FPGA design, when you say we are going to do the STA, which is called as a static timing analysis. So why it is called as static timing analysis? When you say the static timing analysis is going to perform only timing, right? It is not going to perform anything related to functionality. So why it is static? Because it does not require any test vectors. We are not going to pass any test vectors in the STA. Whereas when it is dynamic timing analysis, then we need to pass test vectors also, because it is going to check the functionality as well as timing. That's what we call that as a DTA. Right. What is the advantage of STA when you see? Since it is not going to take any test vectors, it is faster than DTA. But then there are so many considerations that we need to do in STA that we will do one by one. But at this junction, we need to understand that the fundamental goal of STA is to find out the critical paths in the design. Now the question is, what are critical paths? So critical paths are the paths which takes the longest delay. So if you find out which path is taking the longest delay, and if that path meets timing, then we need not to worry about the rest of the paths. So what are the learnings here? What is an STA that we need to know? What is the fundamental goal of STA? Right, the fundamental goal of STA is to find the critical paths in the design. And what are critical paths? Critical paths are the paths which takes the longest delay. So the delay includes what? It includes the gate delay as well as the net delay, the logic delay as well as the wire delay. Okay. Right. Now in STA, what happens is the circuit is divided into different set of timing paths. As I mentioned earlier, you have a source flip-flop, and then you have a destination flip-flop. You have a launch flip-flop, and then you have a capture flip-flop. Now, the STA is dividing dividing the circuit into different set of timing paths. If you see here how they are getting divided, I will show you. Now you can see there are three data type paths you could see. One is from input to sequential element, which is called as input to edge path. The second one from sequential element to sequential element, which is called as register to register path. And the third one is from sequential element to output, which is called as register to output, reg to output. Now, how do we divide these paths? When you say they are divided by considering two things. One is called as the start points. The other one is called as the end points. So remember, these are very important now. So what are start points? When you say the start points are input ports, right? And the clock pins of the flip-flop. These are called as start points. One is the input port, and the other one is the clock pin. And what are the end points? When you say the end points are output port and the data pin of the flip-flop. The data pin of the flip-flop and output port are called as end points. So what are start points? The start points are input ports and the clock pins, and the end points are the output ports and the data pin of the flip-flop. Right now, based on this, we can divide the circuit into different set of timing paths. Now you can see that this is called as input to edge path. Now you can see it starts from an input port, goes through the combo logic, and ends at data pin of the flip-flop. That's what we call that as input to register. Okay. The next one is called register to register path. The register to register path means it starts from the clock pin, goes through the combo logic, and ends at the data pin of the flip-flop. That's what we call that as register to register. And the third one is called as register to output path, where it starts from the clock pin, goes through the combo logic, and ends at output port. We call this as register to output, reg to output. The circuit is divided into different set of timing paths based on start points and end points. And what are those start points and end points? If we see, start points are input ports and clock pins, and end points are output ports and data pin of the flip-flop. So this is very important for us to understand. Right. So now the circuit is divided into different set of timing paths. Then what we are going to do is we are going to find the delay of each and every path. The delay of each and every path is calculated, and we have to find out which path is taking the longest delay, and that path is known as the critical path, which we are going to find out in SDA. That's the fundamental goal. Okay, let us explore the details further. Now, whenever we do any synchronous analysis, definitely we would have come across two important terms. One is called as the setup time. The other one is called as the hold time. Right? In timing analysis, we ensure that the setup and hold, right, should not get violated. We should not have any violation based on setup and hold. Okay, what we are going to ensure here when you say, we ensure the clock and synchronous signals do not arrive at the register input or about at the same time. That means the clock and data are running in the race, right? We don't want the clock to win. That means we'll have a problem, right? So we definitely have a setup time. Similarly, register output does not become unstable. There should not be any metastability issues. And the third one, registers transfers data in a known or guaranteed behavior, because we know that in what behavior we wanted that to happen. So based on this, we are ensuring that the design is not having any setup violations or hold violations. What is that setup violation? What is that hold violation? And what is that setup parameter? What is that hold parameters? What is clock arrival time? What is data arrival time? Everything we will get into the details step by step right now. Let us explore a little further. Now, if we see what is setup time, TSU, the minimum time, the data signal must be stable before the clock. That means you can see minimum time before the clocking event, the data should be stable or must be stable. When you say, that is called as the setup time. You can see that this is a setup time. This is before the clocking event. And the minimum time, the data signal must remain stable after the clock edge is called as the hold time. Minimum time after the clocking event, then the data signal must remain stable is called as the hold time. So between the setup and hold time in this window, in the setup and the hold window, the data should remain stable. It should not get changed. The data should not be changed in this window. That's what we are going to ensure. So what is the basic definition here? When we say it is setup, minimum time, before the clocking event, the data must be stable. And when it is hold time, the minimum time, the data signal must remain stable after the clock edge. When you say, that is called as the hold time. Right. So now based on this setup and hold, let us understand the definition of the data arrival time, what kind of parameters are taken into account, and then we'll also understand what is the meaning of the clock arrival time. So get into the details. What we need to know is like how the launch and capture, or the launch and the latch edges are calculated. We can see that there is a register, that is register 1, and then we have a register 2. We can see that this is the launch edge, right? And then we can say this is the latch edge or the capture edge. That means it is from rising to rising. That is typically one clock cycle. That's what we wanted to know. Typically in this one clock cycle, we want the data to be transferred. Now, what we need to understand here is what is called as the launch edge and what is known as the latch edge in order to find out the data arrival time and the clock arrival time. So what is launch edge here? When you say the edge which launches the data from the source register. Right. So just give me a minute. There was a question in the chat. I will just understand what is that. So what is the first point? Can anyone let me know what exactly you wanted, please? Can you please elaborate it? What do you want as the first point? Okay. Fine. So I will go ahead. Let's see what exactly is required. Right. So let me explain that to you. See here, when you say the setup value, the hold value, as well as you will have the asynchronous behaviors, right? So we need to understand that how we are going to ensure that the design is having the violations. Let us go into the details, right? So how are we going to see that which violation is the problem and how are we going to fix those violations? We will get into it. But now the basic idea is what we need to understand is when we have a edge, right? When we have a launch edge, that means that shows that the edge which launches the data from the source register, that's what we take from rising to rising. And then when it is a latch edge, the edge which latches the data at the destination register. So between one clock cycle, typically in one clock cycle, we wanted between the rising to rising edge, we wanted to ensure that the design is meeting time. So typically in one clock period, we are going to take. That is not the case in all the situations because there may be chances where you will have a multi-cycle path also, right? Let us explore this one by one. Let us first start with what is the data arrival time. The time for the data to arrive at the destination registers, that is register to D input, is known as the data arrival time. When it is a data arrival time, what is very important here is when you say, now this is called a T clock. Right? So data arrival time means that is equal to launch edge where you have launched plus T clock 1. That means this is the delay from this place to the clock input. Only when the clock arrives the first flip-flop, then you can see that it will be triggered. So launch edge plus T clock 1 plus TCO. That is your T clock to Q. This is the transition delay. The T data. What is the time taken from this place to this place till it reaches the data pin of the flip-flop? That's what we are going to understand. The data arrival time is equal to launch edge plus T clock 1 plus TCO plus T data. What are the things that need to be kept in mind here is when it is we are calculating the data arrival time, then it is based on the launch edge plus T clock 1 plus TCO plus T data. What is this T clock 1? When you say this T clock 1 is the time taken, right? So you have to see, right? What is the time taken to reach this clock pin of the flip-flop? Then you need to see TCO. This is nothing but your T clock to Q. Then you also need to calculate T data. That means once the data is triggered, what is the time taken to reach the data pin of the second flip-flop, which is the destination flip-flop, which we need to note down. Then the next information is what is the clock arrival time? So we have seen the data path till now. Now we also need to know what is the clock arrival time. When it is a clock arrival time, what is important is clock arrival time is equal to latch edge. That means you can see that this is the latch edge clock 2. Latch edge, when you say, then you have to see that what is the time taken here. This is the latch edge, which is called as the capture edge, plus T clock 2. You can see that the first flip-flop will get the clock earlier, second flip-flop will get the clock later. We call this as a clock skew. Means clock skew is a measure of difference in arrival of the clock between two successive registers. So in this case, you can see that the first flip-flop gets the clock earlier, the second flip-flop is getting the clock later. So then you can see the clock skew is equal to the time taken for the clock to reach the second flip-flop, the destination flip-flop, minus the source flip-flop. If we do, we can identify what would be the clock skew. So the idea is clock skew is a measure of difference in arrival of the clock between two successive registers. That's what we try to find out now. So the clock arrival time is equal to latch edge plus T clock. So this T clock 2 is nothing but what is the time taken for the clock to reach the second flip-flop that we need to know. Now, based on this data arrival time and the clock arrival time, we are trying to come up with two important things. One is called as the data required time in terms of setup. Other one is the data required time in terms of hold. These are the two important things which we need to bring up here. So this waveform and this circuit is very important and essential for you to understand to find out what is the setup slack and hold slack. Okay? So let us explore this very slowly and understand the principle. Right, when we are applying the same clock, but then there is always a clock delay, right? There is a wire delay, right? So the clock 1 will be, there would be a minimal skew because the same clock is reaching two registers, but then there is a difference in the net delay, right? Because the first flip-flop will get the clock here, there is a net delay which you can see, where the second flip-flop will get the clock later. There is a chance that the first flip-flop will also get the clock later. There is also a negative skew. We don't need to worry about that concept at this junction, okay? So please understand that when you take two registers, there is a minimal skew between those registers because the clock will reach two flip-flops at different times. There are possibilities that we need to understand, right? And at this case, we are understanding only in terms of a single clock, right? The same clock is reaching two registers. I am not discussing about multiple clocks. Right, so we will discuss about multiple clocks later. That means the first flip-flop will get one clock and the second flip-flop will get another clock. Okay, that we will see later. Okay, the minimum time required for the data to be valid before the latch edge so that the data can be successfully latched into the destination register. So that is the meaning of data required time, which is set up. Now you can see that the minimum time required for the data be valid before the latch edge. That means the data should be available, right, before the clock reaches the second flip-flop. That's what we wanted to ensure. So if the data is available here, if the data is ready, then when the clock reaches the second flip-flop, it is very easy for us to move it to the next flip-flop. That means we should ensure that the data should be stable before the clock edge. Now, what we need to identify here is data required time setup is equal to clock arrival time, okay, minus TSU, which is called setup time, minus setup uncertainty. Now, what is very important for us to understand is when we go through the definition of setup time, minimum time before the clocking event, the data must be stable. So in that case, whenever we are doing setup analysis, please understand setup time should be subtracted on the required side. That's the easy way to understand. Whenever we do setup analysis, setup time need to be subtracted because before, the definition is what? Before. That means the data should be available before. That means we should subtract setup time and see whether the data is available. So clock arrival time minus TSU minus setup uncertainty. So the uncertainty are divided into two parts. We will discuss about them again in detail. But at this junction, let us explore two things. One is called the clock skew, which I explained, right? The clock skew. That means it is a measure of difference in arrival of the clocks between two successive registers that we should know. The other one is called as clock jitter. That is nothing but the frequency variation in the clock source. Because sometimes what will happen due to the temperature variations, due to noise, and then due to aging of crystal oscillators, there is a small shift in the clock. That means it can shrink or it can elongate. It won't happen right in next consecutive clock cycles. In 1 million clock cycles or in 10,000 clock cycles, you can see one clock period may shrink or it can be elongated. So that is called as the jitter. So that jitter will also be considered as an uncertainty. So what we are trying to do in this formula is we subtract the setup time and we subtract if there is any uncertainty. And then we note down data required time is equal to clock arrival time minus TSU minus setup uncertainty. Okay, now this is in terms of setup. Second thing what we need to find out is in terms of hold. The minimum time required after the latch edge for the data to remain valid for successful latching into the destination register is called as the data required time hold. In this case, what is important is we need to see that minimum time after the clocking event, the data should be stable. That means after the clocking event means what? After the clock reaches also, the data should be stable. Therefore, whenever we do hold analysis, we should ensure that the hold time should be added. So you can see data required time hold is equal to clock arrival time plus TH plus hold uncertainty. If there is any uncertainty on the hold time, that also need to be added. Now, what is very important for us is two important statements which we should know. One is data required time setup is equal to clock arrival time minus setup time minus setup uncertainty. Whereas when it is a data required time hold, that is equal to clock arrival time plus hold, that is TH, plus hold uncertainty. Now, based on these two, we are going to arrive at two important formula. One is called as the setup slack and the other one is called as the hold slack. We require setup slack and then we require hold slack. What is this setup slack? What is this hold slack? That's what we are going to discuss in the coming slides. Let us explore them right now. Setup slack is equal to data required time minus data arrival time. In simple, how you can understand this, setup slack is equal to RT minus AT. Okay, RT is required time minus AT, which is arrival time. If the required time minus arrival time is a positive number, if it is a positive slack, then we can say that the timing requirement is met. If it is a negative slack, then we can say that the timing requirement not met. Now, what is very important for us is, if it is a data required time when it is set up, minus when you do this, right, RT minus AT, if you get a positive number, then there is no setup violation. If you are getting a negative number, then there is a setup violation. That's the basic idea. Okay. Now, what are the points that need to be addressed here when you say? We also need to consider three important terms here. One is called the process, which is the manufacturing process. The second one is the voltage. What is the operating voltage? And then we also have a temperature. So now we have process, voltage, and temperature, which are called as PVT conditions, we would say. So we should also use this process, voltage, and temperature condition. That also need to be considered. And we should also use minimum and maximum values in the timing delay calculations. How that minimum and maximum is going to affect you while calculating the timing analysis, right? While performing the timing analysis, I will show you in the coming slides. But the easiest way to understand this is setup slack is equal to required time RT minus arrival time AT. Next, we have a hold slack. When it is a hold slack, that is arrival time minus required time. Okay, so it is AT minus RT. What we wanted is the arrival time minus required time should also be a positive number. You should not just imagine that, okay, arrival time minus required time. When you say if it is a positive number, that means you can see that the design is meeting timing. There is no hold violation. But what you should not think is that the required time minus arrival time is a positive number. Arrival time minus required time is a negative number. Like that, you should not think, because we are not going to use the same delay values for calculating setup and hold. So please keep that in mind. Okay, the delay values are completely different. Okay, that's what we are going to understand when we get into the details now. So hold slack is equal to data arrival time DAT minus data required time, which is DRT. In simple, it is AT arrival time minus required time, right? So AT minus RT. Okay, in this case also, we are going to understand about the process, voltage and temperature. Okay, now after all these discussions, we need to arrive at a formula. So this slide is very, very important for you to understand. In this, what we are trying to do is, if you know one line, we can derive the another one. Okay, simple logic is, slack is nothing but minimum something minus maximum something. That's all. First minimum should come, minus maximum should come. In this case, what I told you some time back, for the setup slack, it is required time minus arrival time. Anyway, D is common. You just write here required time minus arrival time, which is DRT minus DAT. Then for the hold, wherever you have DRT, you write DAT. And wherever you have DAT, you write DRT. Reverse you write. So this DRT will come here, this DAT will come. This is the way how we are going to calculate the setup and hold. Simple logic is, setup slack is equal to required time minus arrival time, and hold slack is equal to arrival time minus required time. But simply we should have minimum minus maximum. That is common. There is no change. On the left hand side, you should have minimum. On the right hand side, we should have maximum. But what would be changed is, when it is set up, minimum data required time will come, and data arrival time will come on the right hand side. Whereas when it is hold analysis, data arrival time will come on the left hand side, and data required time will come on the right hand side. Right. So after noting down this formula, we are going to do a paper and pencil exercise to find out whether the design is having any setup violation or hold violation or what. How are we going to solve the issue? So that means what and all informations we wanted. We wanted the setup time of the flip-flop. We wanted the hold time of the flip-flop. We wanted the T clock to Q of the flip-flop. We want the wire delay. We wanted the logic delay, that is the combinational delay, TPD max minimum. So if someone provides all these details, we can definitely calculate the delay and find out which is the critical path and what is our requirement, whether that requirement has been met or not, we can find out. So to solve that and to get an idea, there is a paper and pencil exercise example that is provided to us right now. Let me explain the background, and then we will try to solve that parallelly and understand whether the design has any setup violation or the design has any hold violation. So if you go through the circuit, you have the T minimum 1 nanosecond and the T max 2 nanoseconds. And you can see this is called as the T clock to Q. You cannot control the setup time and hold time because that is available in the library, right? So we need to see that information is fixed. Okay, the tool will take the setup time and hold time. What we have control is, we have a control between the flip-flops, right? There is a combo between the flip-flops. So good RTL coding styles will ensure that the delay can be reduced, and whatever requirement you have, you can definitely beat. Okay, there are different the techniques that could be adopted. But at this junction, just ensure that the setup time and hold time is fixed. Okay, we cannot modify anything there. Okay, let us start here. Now we can see there is a T clock to Q, there is a minimum value, and a T clock to Q maximum. So you can see that for everything you have a T minimum T maximum, T minimum, T maximum, T minimum, T maximum, everything is there. Okay. Sometimes the wire delay can be ignored. Okay, but in this case, just note down that there would be definitely a wire delay. We will calculate the path delays, right, one by one. Let us start. Now the setup time is 4 nanoseconds that is provided, and the hold time is 2 nanoseconds. So as per formula, setup slack is equal to minimum delay along the clock path minus maximum delay along the data path. That is nothing but minimum data required time minus maximum data arrival time. This is what we need to find out. That is equal to what? Let us put the values one by one. So now minimum data required time. That means if you see the values that is present on the clock side, that is nothing but minimum delay along the clock. That is on the requirement side. Please understand, on the requirement side, you have to subtract the setup. Okay, right. First, let us start with the values. We want this design to work at 50 megahertz. That means the time is 20 nanoseconds. So the clock value is 20 plus minimum delay 2 nanoseconds plus minimum delay 5 nanoseconds plus minimum delay 2 nanoseconds minus 4. That means setup time need to be subtracted. So this is on the clock part. Take all the minimum delays and then subtract the setup time. Now we need to see the data path minus maximum delay along the data. When it is maximum delay along the data path, when you say, see here, right, 2 nanoseconds plus 11 nanoseconds, because this is maximum, plus 2 nanoseconds plus 9 nanoseconds plus 2 nanoseconds. We add these values, 2 nanoseconds plus 11 nanoseconds plus 2 nanoseconds plus 9 nanoseconds plus 2 nanoseconds, which provides you here 25 minus 26, which is minus 1 nanosecond. That means you have a setup violation. The design is expected to work at 50 megahertz, but it is not working. Why? Because you can see the slack is having a negative value. Now, what you will think in your mind immediately? What is our easiest way to solve this problem? When you say we will increase the clock period, that's what we will think in our mind. Okay, we will make this to 21. So 26 minus 26 will become 0. Then problem will be solved like that. But for paper and pencil exercise, that could be a good idea for you. You can increase the clock period so that what will happen is you are expecting the design to operate at 50 megahertz. That may not be the case. The design is expected to work only lesser than 50 megahertz. Why? Because you are increasing the clock period. What is the easiest solution is, okay, I will increase the clock period and ensure that, okay, the design is not having any setup violation. Okay, that would be very good only for the paper and pencil exercise. That is not a desirable option. Okay, it is an undesirable option when we get into the timing analysis, right? But to solve that, okay, at this junction, how do we solve? It's like the solution what I told. Let us try that. If you make the period longer, what will happen? 21. You can see that the design is expected to work at 50 megahertz. Since you make the period as 21, it is expected to work only at 47.6 megahertz, not 50 megahertz. From this, what did we understand? When you say, if you increase the clock period, there would be definitely an impact on the frequency. Now, what is also very important for us to understand, that is not a desirable option, because we should think that there will be multiple techniques that could be done in order to overcome setup violation. Whereas increasing the clock period is always an undesirable option. So after entering into the timing analyzer tool, we will identify and see that what kind of other techniques that could be adopted. Let us explore the hold analysis for the same circuit. Now, if you see the hold analysis of this design, you can see that T equal to 20 nanoseconds, that is 50 megahertz. But what is the formula is minimum delay along the data path minus maximum delay along the clock path. So we have to do reverse, which is nothing but arrival time minus required time. When we need to do that, what happens is when it is arrival, that means here you can see that minimum data arrival time. So in the data arrival side, we are supposed to take the minimum value. So 1 plus 9 plus 1 plus 6 plus 1. Take all these values. Please only take the minimum value. 1, 9, 1, 6, then 1. Minus, please understand, on the required side, hold time should be added. Right? On the same logic, when we do setup analysis, setup time need to be subtracted on the requirement. So now on the requirement, you should ensure that hold time should be added. Here, if you see the data required time, if you say on the required side and on the clock side, take the maximum value 3 plus 9 plus 3 plus 2. Now we can see 18 minus 17, which is 1 nanosecond. Now there are two questions to be answered. One, the design is not having a setup violation. The design is having a hold violation. That is one case. Now, in our case, what happened? The design is having a setup violation. There is no hold violation. But there may be another case where the design will have both setup violation as well as hold violation. But what is our responsibility here? The design should not have any setup violation. It should not have any hold violation. Both should not be there. Only then we can proceed. So what is our responsibility here? Whenever we give the requirement, whenever we give the clock value, after creating a base or a virtual clock, we should ensure that the design is meeting timing. That means it should not have any setup or hold violations. That is very important for us to address. So in this case, what happens is the setup is having an issue. To solve that, what we did is we increased the clock, but we didn't do anything for hold. We kept as it is, like 20 nanoseconds only, but then the design is not having any hold violations. What are the things that need to be taken away? By increasing the clock period or by reducing the clock period, it is going to affect only the setup, not the hold. You have to be very careful because the hold analysis is done on the launch edge. There is nothing to do with the clock period. Okay, please keep that in mind. Now let us explore another example here. So this was having two flip-flops and then you have multiple delays that need to be involved. Let us take a very simple design now. You take a design where the T is 10 nanoseconds. We wanted the design to work at 100 megahertz. You have the register, which is the T clock to Q, 2 nanoseconds. TPD max 5 nanoseconds, TPD minimum 3 nanoseconds, and then you take setup time 2 nanoseconds and hold 1.5 nanoseconds. What is the formula? Setup slack is equal to required time minus arrival time. So minimum DRT minus maximum DAT. So what we can say is 10 plus 1, 10 plus 1 minus 2. That means we need to subtract the setup. Now, when we do that, we are getting what is the value? Let us see. Here you can see on the required time, you take 1, then plus 2, and then you can see 5. This is the maximum. And you are getting the value of 2 nanoseconds, which is a positive value. It means there is a positive slack. For the same circuit, let us do hold here. Minimum data arrival time minus maximum data required time. So that means we will try to do 1 plus 2 plus 3. This one you take because this is the minimum value 3 minus what we are supposed to do is 1 plus 1, and then you should add the whole time, which is 1.5. You can see 2.5 nanoseconds. That means the design is not having any setup violation. The design is also not having any hold violation. Now let us consider, instead of 10 nanoseconds, if I wanted to change my time to some other value, will there be an impact? When you say definitely, because now the design is working at 100 megahertz. But if you wanted to change your time, then automatically it will get affected. Let us try that. If you wanted to change this to 6.6 nanoseconds, now you could see 6.6 we applied instead of 10. Now you can see it shows minus 1.4. That means it is showing a negative number. Whereas, same when we try to do with hold slack, it doesn't change. What did we understand from this is by increasing the clock period or by reducing the clock period, there won't be any impact on the hold analysis. There would be an impact only on the setup analysis. Please keep that in mind. And what are the other takeaways here for us when you say? It is very critical that we should ensure the design is not having any setup violation and the design is not also having any hold violation. That need to be taken into account. So this is what is the background that we need to understand. And based on this, how the timing analyzer works, that's what we are going to understand in detail. So till now we have understood the concept of the timing analysis, and we have done a paper and pencil work to identify whether the circuit has any setup or hold violation. So what are the key takeaways when you say? Number one, we should know what are the different set of timing paths. For that, I explained you about the input to register path, register to register path, as well as register to output paths. Then we have seen what are start points and end points. And then we have understood what is the data arrival time, clock arrival time, data required time in terms of setup, data required time in terms of hold, and then we have identified how to find the setup slack and the hold slack, which is nothing but required time minus arrival time in one case and arrival time minus required time in another case. Now, let us explore the details of the timing analysis. So what is the timing analyzer when you say? In the earlier discussion, like yesterday, we didn't perform any timing analysis. So whenever you take a design and we are not applying any timing constraints to it, you can see in the transcript or the console window that the design has not been applied for any timing constraint. That means it will show that the design is not having any setup constraints, as well as it does not constraint for hold. So it is our responsibility to ensure that the design is not having any setup or hold violation. So we should provide the details and ensure that that should be taken into account before we go to the next step. So what is available in the timing analyzer right now? You have the constraints tab where we can apply the constraint. That means we can specify the constraints. And then we have a reports tab where we can report, we can identify the report. That means we can check whether the design is having any violations that we can check out. So that means there are two important commands which we are going to discuss in detail. One is called as the reporting the clock, right? Whatever we created the clock, whether it is getting reported properly or not. And then we should also check whether the report timing, that means the design is going to provide you the value of setup slack and hold slack, that we will identify is that proper or not. We are going to get introduced to two timing analyzer flows. One is using the tool itself, right? We have to follow the step every time you open and use the timing analyzer. And the second one is timing analyzer integration into the Intel Quartus Prime design software flow. So now we are going to understand how timing analysis is enabled and how it is working in the design flow. I'm going to show you a simple demo of how the timing analysis can be enabled. That means how that process gets enabled and then how it works in the design flow. I'm going to show you a simple example. Right. So to get into the timing analyzer flow, we need to understand that what are the steps that need to be taken into account. Number one, we should generate the timing netlist. Then we should apply SDC. That means it is a synopsis design constraints. We are going to apply the constraints, and that can be given through GUI, or it can be applied through the tickle console. We can update the timing netlist. We can generate timing reports. So we are going to see all the steps. We are going to apply the constraint, and then we are going to see that once that constraint is applied to the design, what is the impact of that? That we are going to see. That means we are going to generate the timing reports. After generating the timing reports, we are going to analyze it. There are 3 steps I explained to you. First thing is we need to analyze. Second thing is we have to debug. The third one we have to validate. Okay, so we need to validate the timing performance of the design. Finally, if we wanted, we can save the timing constraints. Otherwise, it can be kept what? Optional. So that means there is an option that write SDC file. You can write the SDC file, and then you can use it for later viewing. That you can modify it later, and then you can integrate that to the Quartus Prime design software. So how are we going to approach this method? When you say there are different things that need to be followed. Let us explore that one by one. You take a synthesized design, and we use a timing analyzer to specify the timing requirements. We configure timing analyzer in the Intel Quartus Prime design project. And again, we are going to perform full compilation. That means we need to run the fitter once again and verify the timing in the timing analyzer. So now when we apply the timing constraints, it is very essential that the design has taken those constraints or not. So it has accepted those constraints, then we have to identify that there are no setup and hold violations. And what we should do is we should take that constraint file, integrate that to the Quartus Prime design software, again perform fitter operation, and ensure that at the end of the fitter, the design is not showing any violations, so that we can go to the next step. How it look like? You need to see the tool. Now you can see what are the steps that need to be followed. So if you see here, yesterday I explained that we need to perform different fitter operations. There are 4 stages in a fitter. So you have a plan, you have a early place, and route. These are the 4 stages that are available in the fitter. Now what we wanted to do is called as the timing analysis, which is the sign-off, which is very, very important for us to solve the problem. So we need to perform timing analysis, which is very critical and important at this stage. Okay, what are the important information that need to be kept in mind? We are ensuring that the design is working at the desired frequency or not. That is very important. Second thing is we should also ensure that the design is not having any violations. So these 2 we can think. But then you have to understand that the functional simulation, what we check the functionality, right? That one is different than what we are going to do now, which is timing analysis, where we are not going to check the functionality. We are going to check only time, not functionality. In the timing reports, there are 2 ways you can see that. One is after performing synthesis, that is the post map netlist, we can see whether the design is meeting timing. And the other one is after fitting, that means after performing the fitter operation, placement and routing, we can check whether the design is meeting timing. So this is very, very important for us to do. So the timing results would be available in both Intel Quartus Prime design software compilation report, as well as in the timing analyzer G. The timing analyzer includes more extensive reporting capabilities. So here what we are trying to do, we can create reports while creating constraints before fitting. That means after the synthesis process, we can check whether the design can meet timing requirements. And we can create reports after fitting to verify that the placed and routed design meets the timing requirements. Right. So now we can see what kind of things that need to be taken into account when we say we have to see there are 2 important things that need to be kept in mind. One is you can see the slack value, the worst negative slack. It will show you a negative number. We could also see there is a TNS, which is called as a total negative slack. What is the total negative slack when we say? The total negative slack is the sum of all negative slack numbers in specific clock domain. In one clock domain, if I have one path which is not meeting timing, if I say which is the critical path, if I say that is called as the worst negative slack. If I add all the slacks which are negative and I see what is the number, that is called as a total negative slack. You can also see the worst negative slack WNS. We can also see the total negative slack, which is a TNS. Both are required in the summary reports. Right? So this is very important at this junction because yesterday, while doing the first project in the lab, right, where we performed pin planning, we did through GUI. And in the second lab, when we performed for the LabsLAN setup, we did the pin planner using the tickle console. We copied all the tickle commands and pasted that in the tickle console. Now also, there are two ways to solve the problem. One is you can use the GUI to see the report immediately, and you can also use the tickle file for repeatability. Both are available. You can use the GUI and you can also use the tickle file. But I am going to introduce the GUI first because we are not very sure and confident about the tickle commands. We don't know what is the syntax to be typed. But after getting some hold on the GUI, we can use the tickle console for repeatability. That is definitely possible. And what is another important thing that need to be noted down here is after we apply the constraints, we wanted to see the report. For that, we use a command called as report timing command. This report underscore timing command will provide you the details of all the paths, right, with respect to setup, with respect to hold. You can select either setup or hold. Based on that, it will show. By default, it will try to show the number of paths, the worst paths, but then you can increase it based on whatever we wanted. In the GUI, you can change that 10 to 40, 50, whichever you want, you can modify. That is also possible. Okay, so once you provide the details, like if you click report timing, you can see what is and what is all these informations we can provide, and then information for project. Right, you can see the report. I will show that to the demo. Here you can see there is a launch clock and there is a capture clock. There are chances that the launch clock and the capture clock may be same. There is a chance that the launch clock may be different, and the latch clock, that is the receiving clock, may also be different. So you will have a single clock domain. You will also have a multiple clock domain. So please keep that in mind. And what I explained about the clock skew, that you can see that here, which is a difference in arrival of the clock between two successive registers. I told you that information is available. Right. So two more things before we go to the next session. Whenever we take about the synopsis design constraints, which is called as SDC netlist terminology, we need to know how we apply the constraints. So one is called as cell, then pin, net, port, and registers. So how are we going to write them? Get cells, get pins, get nets, get ports, and get registers. So if you see how the netlist are taken into picture, here you can see it is a cell, it's a pin, right? You can see, then you can see net, and then you have port. How do we call them? If you wanted to get the port, we can say get port. If you want to get the pin, we'll say get pins. If you want to get the cell, then we will say get cells. Right? If you want to get the net, we can say get nets. So all those informations are available in the SDC netlist. That means how are we going to query the database inside the design? And we say we can use these specific logics. We can use get cells. You can use get pins. We can use get nets. We can also get registers. Whichever we want, we can take. We call this as a SDC netlist example. Let us go to the first example, and then I will enter into the demo session. What we are going to learn in this is how do we create a clock. So the create clock is the command which helps you to create the clock for the specific design. What is the syntax? Create underscore clock hyphen name, name of the clock hyphen period, period of the clock. If it is not 50% duty cycle, then we should also provide hyphen waveform, rise and fall. And we need to provide the target. How it will look like? Let us see that here. Create underscore clock hyphen name, name of the clock, hyphen period, period of the clock, get underscore ports. What is the name of the clock that is provided in the RTL? That value need to be provided. And you can see create underscore clock hyphen period, period of the clock, hyphen waveform. Right here you can see it is not 50% duty cycle, it rises at 2 and again it rises at 12 and it is not having 50% duty cycle. If that is the case, then we can provide hyphen waveform. It starts rises at 2 and then again it falls at 8. That means if you wanted to get 10, then it should again rise at 12. So that means 12 minus 2, which is nothing but 10. So this is the way how we can do that. We'll stop here and then I will walk you through the next section, which is called as applying the timing constraints in the Intel Quartus Prime timing analyzer. Let us approach that method and then we will come back to the session. Right? So what's the takeaway? You can see that how are we going to create the clock, and we are also going to see how do we ensure that the clock is taken into account, report clocks, and we should also see how do we analyze the timing report, which is called as report time. Right, so let us move on to the next section. I will open the Quartus Prime design software. Let us create a new project. Then we will apply the clock for a design. So you click here, new project wizard, and say timing for the counter design. Okay, let us take simple example. Just we will apply only the clock. You can provide here counter, create it, let it be empty project. Okay, next, no need to add any files here. Please select the Maxton device, NM50 DAF 484 C7G. Select the device, say next, finish. Okay, right, now let us go and find out. Now file, now we should say new and say Verilog HDL. Let us take a simple example. As mentioned there, you take a counter. So input, I say clock, then reset, then we'll say output reg down to 0, you take Q. So always, then we'll say at percentage of clock, comma, negative of reset. So begin, let's say if reset, Q is equal to 0, let's say else, so Q is equal to Q plus 1, and say end. Now let us save this file. So file save as and say counter.v, ensure that it is saved. Now first let us do analysis and elaboration. Okay. Now, if you go to tools, go to the netlist viewers and say RTL viewer. Now we can see that there is 3 down to 0. There are 4 flip-flops. In the RTL schematic, we can see which is technology independent. That does not show that what kind of lookup tables and registers are used in the design. Okay. In order to do that, first we will perform the other process. Let us do the entire compilation. Now you can see in the compilation report, it shows that how many number of registers are used. You can see there are 4 registers, and it shows that how many number of logic elements are used. Okay. Now let us explore this in detail right now. So how do we see the output here, right? You can see the RTL netlist in terms of the technology independent schematic. Now, as I mentioned, you can see technology map viewer post mapping. Here you can see that there are 4 registers, Q of 0, Q of 1, you can see Q of 2, then Q of 3. So you can see there are 4 registers that are available. And we can also see this after performing placement and routing. Again, we can go to the netlist viewers and say technology map viewer post fitting. And when we expand that, we can see that register to register. Q of 0, Q of 1, Q of 2, as well as Q of 3. So between the registers, you can see there is a combinational logic block. Okay, you can see Q of 1, Q of 2, then Q of 3, all those things you can see that. Now, what are the operations that it has been performed? We have seen the full compilation report. But then you can see the timing analyzer. It shows that the logic is we have not applied any timing constraints to the design. So if you see in the console window or in the transcript, you can see that design is showing that timing requirements not met. That means you didn't apply anything to provide here. So you can see that no specific logic. So you can see design is not fully constrained for setup requirements, and the design is not fully constrained for hold requirements. What we have not done so far is like we didn't apply any constraint. That means we didn't create a clock, and the tool is not in a position to provide you that whether the design is having a setup violation or there is a hold violation. So what we need to do is like we should enter into the timing analyzer and apply timing constraints and see what is happening. Okay, so we are going to deal into the details in the afternoon, but then I will just show you what are the important commands that need to be addressed here. So you should go to tools. What and all we did yesterday in the tools tab, you can recollect that run simulation tool, and we did RTL simulation. And we did netlist viewers, RTL viewer, technology map viewer, post mapping, technology map viewer, post fitting, state machine viewer. And we also did chip planner yesterday. But what is our focus today is we need to do timing analyzer. Click tools and say timing analyzer. You can see that welcome to the Quartus Prime timing analyzer. And what is very important for us is we should set the process voltage and temperature. So first you click here on the left hand side, you can see create timing netlist. Just double click that. So there is some process voltage and temperature and information that is set for you. In the lab manual, it is very clearly explained what is these models. At this junction, let us take the default model. We don't need to worry about what are these things. While doing the lab, you will be coming to know that what is the meaning of the specific process voltage and temperature and why we are choosing that kind of timing netlist model. But now let us be having the same default model. Let us set the operating conditions as it is. We don't want to change it. What we have learned in the concept is there is a constraint tab, and then we have also seen a report tab during the conceptual explanation. We can try that right now. So when we click constraint tab here, you can see create clock, create generated clock, set clock latency, set clock uncertainty, remove clock, set input delay. You can also see set clock groups, which are asynchronous clocks, set input delay, set output delay, set false path, set multi-cycle path, set max delay, set minimum delay, read SDC file, write SDC file, minimum things are there. This is called as the constraints tab. And then the next one, if you click reports tab, here you can see the multiple reports. Report setup summary, hold summary, recovery and removal for asynchronous paths. Then you can also see multiple informations on the data sheet, device specific information, diagnostic reports, and then you can also see the custom reports. There are multiple reports tab that is available. You can enable the reports tab from this tasks tab also. But now let us understand how do we apply the constraint and how do we analyze the timing report. That is our major information. At least the basic constraints we can apply, but then we can understand how to apply the timing exceptional constraints like a multi-cycle path constraints and false path constraints. I will explain you in detail in the afternoon. After the session, we can also do the hands-on. Right, let us start with the first constraint. How do we apply now? You click the constraint, and the first one is called as the create clock. So we just say create clock. The moment we click create clock, it opens a dialog box where we need to apply the name of the clock. So the name of the clock can be anything, whichever you like, that can be provided as the name. But then when we are providing the targets like the get ports, then the name of the clock should be the name of the clock which we provided in the RTL. So in the RTL, what we have provided is CLK. That should be the name. That should be the name, right? That should be the target here. Clock name can be anything. For example, if I say here clock here, this can be taken. The moment you type clock here, you can see that there is an SDC command generated, which is the synopsis design constraints command. Create underscore clock hyphen name of the clock hyphen period of the clock. That is the syntax. So create underscore clock hyphen name of the clock is CLOCK hyphen period of the clock is 10 nanoseconds because I didn't specify any rising and falling for waveform. Right, it can be a 50% duty cycle so that it shows here 0 and it falls at 5 and rises at 10. Okay, now what is very important for us is we need to attach this clock to the port. To which port? When you say we have a CLK that is available in the RTL, to that port we should attach it. So you can see there are 3 dots on the right hand side. Just click that and you can click here list because there is a wildcard available there on the filter. Just say list. You can see all the ports are getting listed. Just click only the clock, okay, and click this greater than symbol, which will bring the clock on the right hand side so that we can say okay. So that would be added. So just bring only that here. Otherwise, if you see here, get underscore port, so star is there. We don't want everything because I wanted to generate only the clock. So just bring that here, select it and say okay. Now what we have done, create underscore clock hyphen name of the clock hyphen period of the clock, get underscore ports clock. That is the syntax. So this is the way how we can create a clock. Now this command, STC command, can be reusable. We can reuse this create underscore clock command in the tickle console. So we can create a tickle script and then you can modify the value and then you can rerun. But since we are doing this for the first time, let us explore directly in the GUI only. So now after generating everything, what we should do is you should click run. The moment we click run, you can see here create underscore clock hyphen name of the clock hyphen period. Then you can see period of the clock. Then it shows get underscore ports, then clock. That's what is provided. All the informations are provided to us right now. So create clock hyphen name of the clock hyphen period of the clock. Then we have provided get underscore ports, then clock is provided. Okay. Now what is the guarantee that the clock what we have provided, so the value that has provided is taken by the tool? That we have to check, right? That is very important for us to cross verify whether the value that has been taken by the clock. So either there are different ways of approaching it. First, we will approach them in the GUI only. Okay, there are commands that we can type in the console also. So the moment we give the create clock command, you need to expand the task pane, and here you can see on the diagnostic tab, you can see there is a command called report clock. That's the first command. We can double click that. That will automatically take you to the clock summary. Here you can see clock, and the name of the clock is place, and 10 nanoseconds is the period of the clock, and the frequency is 100 megahertz. And what is the target is CLK. That is the value. That is the name of the clock which we provided in the RT. Now, two important things we learned. One is we need to specify the clock. That means we need to create a base or a virtual clock. We provided that. Second information, we need to verify whether that clock which we have created is taken into account. We should report the clock. So report underscore clocks is the command. Create underscore clock is the command. So we can type those commands directly in the console window also. Right? We are trying to do that in the GUI. Later, after getting confidence, we can directly do that in the ticket console also. Right. These two steps are done. What is the third step that we need to do? Is we need to identify the timing. We should check whether the design has any setup or hold violations with respect to only clock. Only we are just checking register to register paths. Later we can understand how to constrain input to register paths as well as register to output paths. That we will do one by one during the lab session. Okay. But at this junction, let us see how we are going to identify the timing. So in the same task tab, you can see there is a custom report tab where you can see the first command, which is called as report timing. When we click that, you can see it shows setup, hold, recovery, removal. So we wanted to do the setup analysis because it's a synchronous design. And report number of paths, if you say it is 10 by default. If you wanted to expand it to 100 or 500, you can change it. Now we can see setup. Report number of paths by default 10. And for what analysis we wanted is the setup analysis. And just click report timing. First, we will see the setup analysis here. After clicking setup and say provide the timing report, you can see clock. That means it is RT minus AT, that value. And the from and to path. And in our case, the launch clock, that means that is also clock. And the latch clock, the capture clock, that is also clock. Now, in the relationship, if you see, it shows 10 nanoseconds. That's what we created. And you can see the clock skew followed by the data date. In the path summary, you can see it shows that the data required time minus data arrival time. That means it is DRT minus DAT. So the data required time minus data arrival time should be a positive number. Therefore, the slack is a positive number. We can see that. And as per our discussion, that the launch clock and the capture clock are the same because they're single clock domain. Now, how do we explore this statistics? That is very important for us. We need to understand from where these delays are calculated. Okay, so because you need to know that where is that setup time, what is that hold time, what is the logic delay, what is the wire delay, all these informations we want. We will see that one by one. On the right hand side, if you see, you can see the waveform also. It shows that the launch, which is 0 nanoseconds, and then you can see the latch, the capture, which is at 10 nanoseconds. That's what we give. This is called as the 1 clock. That's what we specified. Between the launch and the capture, we wanted the design, whether it is meeting timing or not. Okay, what informations you could see? You can see the clock delay. You can see the data path delay. Right? So the clock delay, data path delay, everything when we say, then we can identify what is the slack. Till what time the data would be stable. That information we can see. Till this place, the data would be stable. You can see that. Okay, now let us explore the statistics tab. At the summary tab, we have seen shows from to launch, latch, data arrival time, required time, slack. Move on to the statistics tab here. Just click that. When we click the statistics tab, setup relationship 10 nanoseconds. And here you can see clock skew. That information is provided. And you can also see the data delay. And what is very important, there was a question, right? So how do we control? When you say what we can control is, we can control the combinational delay between two flip-flops. You can see the number of logic levels is 1. For example, let us take, if the number of logic levels is 5, let us take an example. The meaning is, it has to cross 5 logic levels to reach the second flip-flop. What is the chance? Before it crosses 5 logic levels, there are chances that the clock can reach the second flip-flop. Therefore, it would be a slow logic path. We have to be very careful. Okay, that comes because of our poor coding style. If you write a Verilog or a VHDL or a system Verilog code where between two flip-flops, if you have more number of logic levels, then there are wide chances, right, that the design may not meet time. You will have a setup violation. You have to be very, very careful. Okay, we will have different cases that I will discuss in the afternoon. But at this junction, just understand that the number of logic levels should be a minimum number. In our case, it is only 1 logic level. So then there is no problem. Right? What are the informations that need to be noted down? I showed you right now. The number of logic levels is 1. And you can see what are the delays that need to be taken into account. You can see, I see the interconnect, and then you can see the cell delay. And then for the data side, you can see the interconnect, as well as the cell delay, as well as the T clock to Q. All these informations are calculated. And on the data path, you could see how these informations are also calculated. This is on the data arrival path, and this is on the data required path. You can see that. And you can see the setup time, TSU. Okay. And you can also see how this is calculated. On the hold, you can see the hold analysis. But here on the data required point, you can see the setup time. That is the value that is provided. All the informations are available along with the waveform. With the waveform, you can see that how that is taken into account. The path summary, statistics, data path, waveform. All 4 informations we look into the logic right now. Okay, what are the other informations that we need to note down when we say? You have the slack value. We have from, then we have to node. Now, what is important is we have to explore the path. Okay, which path is that? That we wanted to know. How do we explore these informations here? You can select the slack value. You can see which is the critical path. When you say the critical path is the path which is having the longest delay. Which is the longest delay is this? Because this is the one which is very near to 0 for us. Right? Because if you see this path is 9.260. But this path is having 8.85. Okay, so which path is having the longest delay? That path will come on the top. Okay, so that path will be very near to 0 for us. But in our case, 8.853 is a huge number. It's a big number for us. No worry. But then what you need to understand is the first path, what it comes is the critical path. Right now, when I right click this 8.853, you can see that locate path. We can locate this path in three important places. One is called as the chip planner, which we learned yesterday, and the technology map viewer, and the third one is the resource property editor, where you can see that which resource is used, that we can see that in which particular coordinate it is available. All these informations we can see. Let us understand one. In the locate path, you have to say locate in chip planner. Okay, first you click that in chip planner. It will take you to the chip where the path would be available. So whatever paths that are available, that could be seen in the chip planner. So the informations of the path that could be seen here. Whichever paths are available, that information you could see here. Also, on the down, you can see that which path is that. If you expand that right hand side, which shows the what is the arrival clock, what is the arrival data, and what is the required clocks. When you expand it, you could see that. What is the register, the located paths, what is the slack value, what is the arrival clock. So if you expand that, you can still see that. What is the arrival values, right? And what is the data arrival time? So clock arrival time, data arrival time, and then the clock required time. Everything we can see here for that particular path, and we will get an idea of how the tool calculated the timing for all these paths. This is one. Second important thing which we need to see is the technology schematic, because that will tell you that between two flip-flops, what information is available, how many number of combinational logic information is available. Go to locate path and go to the technology map viewer. When we take the technology map viewer, we can see this is the flip-flop and there is combo logic. Because when you say number of logic levels, it showed only one. That means there is only one logic level between two flip-flops. Therefore, you can see there is a flip-flop launch and there is a flip-flop capture. Then you can see there is only one logic level between these two. And this is the interconnect delay and this is the cell delay. Interconnect delay, cell delay, all the information we can see. This is on the technology map viewer we say. Okay, what is the another one that could be possible? It's called as the resource property editor. So locate the path in the resource property editor. If you open that, you can see that. You can see the entire path here. So how it crosses, how it goes through the combo logic, and how it reaches the register. That information you can highlight and see. Okay, so this is the way how that would be taken. So whichever path we wanted, that information you can see. And that shows that this is the start and it goes through the combo logic. All the informations we could see for a specific path. So in detail, you can get multiple informations of each and every register. So you can see that, okay, so from where it starts and how it goes and then ends the data pin of the flip-flop. Now we can see all the three registers. Right, interconnect delay. Interconnect delay is your net delay, right? How you connect it, and then you have the logic delay, right? Every flip-flop will have three delays, right? You will have T clock to Q, that is called your transition delay, followed by setup time and hold time. And every gate or a lookup table will have a combo delay, right? So that is called as your cell. Now you have the cell delay. You will also have the interconnect delay, which is the net delay. We have to, when I say delay, then you have to add the interconnect delay, net delay, as well as the logic delay, gate delay. Both need to be added. The data delay plus the net delay, both need to be added. Okay, right. Now, what are the informations we have seen here is we have just explored what are the different possibilities of exploring this report, right? What are the other informations? Now, one information is I have seen the report and the design is not having any setup and hold violation because we applied only basic constraints, only the clock constraints. We have not constrained input to reg path and then reg to output path. We didn't do any other paths constraint. But then at this junction, what we can also still explore is we need to save the results into a file. That means we wanted to write a SDC and we wanted to open that. Yes, that is also possible. And we wanted to create an SDC directly for the design. That is also possible. Both ways, it could be easier for us. But when we wanted to create our own SDC, we have to be very careful because we should be thorough with the constraints, what to apply, and we should be very thorough with the command syntax, right? Because sometimes it will help you. The tool will help you to do that, but then still we should be very, very careful, and we should not give any wrong information to the tool. Because if the constraint is having a syntax error, then the constraints will be ignored by the tool, where you may not have any impact of that command on the timing analysis. So it is always very critical and important to try that in GUI, apply that in the command prompt, get an idea, then you try to create your own set of constraints. Right, let me take you to the next logic. When we click the constraint, you can see down, write SDC file. Okay, the moment you say write SDC file and say OK, automatically the SDC file would be written. Where it would be available when you say, you can go to the drive, your C drive, and say timing counter design. Inside that, you can see there is a counter.out.ftc file. You can open that FTC file, where you can see create underscore clock, hyphen name of the clock, hyphen period of the clock. The information is available. First, what we have done is create clock, and you can see create generated clock, set clock latency, set clock uncertainty, input delay, output delay, clock groups, false path, multi-cycle paths. Most of them we are going to do that in the lab today. But then what is very important is how this TC file can be saved. That information we should know. Right. Another important information which also is very much required is we wanted to create the STC file directly from the file. When you say yes, that is also possible here. How do we do that? File, you can select here new, and you can also see there is a synopsis design constraints file. When you click the synopsis design constraints file and then say OK, it automatically provides you a text editor where you can type the constraints. If you have a doubt after create clock what I should do, then the tool will help you to provide the details of the syntax. So after the moment I say create underscore clock, you can see that it shows that hyphen name of the clock, hyphen period of the clock, and also it shows that whether you wanted to provide a waveform or whatever information you want. The information is required because that will help you. So hyphen name, I should say name of the clock. When I say hyphen period, I say period of the clock. Then I should say get underscore port. So I should skew what is the port, this information, and then I should say clock like this. Then I can go to the next one. So this is the way how you can create. You can see here create underscore clock, hyphen name of the clock, hyphen period of the clock, get underscore ports, clock we have given. It shows that stc1.stc. If you wanted to save this, you can say file save as, and you can save it in your design. And you can read this stc file and then we can continue the operation. So there are multiple possibilities what we have right now. Okay, what we have learned in this particular demo is how to apply the clock constraints for the design. What is very important and essential, which we also need to understand before we get into the details of the timing exceptions and multiple clock domains and clock domain crossing, is we also need to know how to constrain a pure combinational design. Because in the yesterday's logic, what we did, right, we had a design in which it was a pure combinational logic path. Let us take an off adder or a full adder or an AND gate, whatever you do, that does not have a clock. So whatever paths we have discussed so far is that it can have a start point where it starts from an input port and ends at the data pin of the flip-flop. And it starts from the clock pin of the register and ends at the data pin of the flip-flop. It starts from the clock pin and ends at the output port. But now what kind of path we are discussing right now is the design in which it is a pure combinational logic path where it does not have any flip-flops in between. If that is the case, how are we going to constrain a pure combinational logic path? That's what we are going to understand. That will give you a good idea of how the tool takes the information, and we will analyze those paths in detail one by one. Let me take you to the second demo, and then we will come back again to the presentation, and then I will hand over to my colleague Bhaskar, and he will continue with the clock domain crossing. Right, let us start right now. I close the project, and we will create a new project with that. So timing for a combinational design, we can say. Timing combo design. And let us take an ad. Let it an empty project. Don't need to add any files, and then request you to do max 10. So file, new, and say Verilog HDL, and say module adder. So input, then I say A, then B, output, say sum and then carry. Let us take two things and then say assign. Sum is equal to A XOR B. Then I say carry is equal to A and B. Let us take something else. So let us save this file. And let us continue with analysis and elaboration first. Okay, right. Let us go through the netlist viewers and then see RTL viewer. You can see there is an XOR gate and an AND gate, which is an adder example. But then let us complete the process by performing compilation. Right, if you can see here, total number of logic elements it shows and total number of pins it takes, like A, B, sum and carry. And then you can see it shows the timing analyzer because the design is not having any requirement. So design is not fully constrained for any setup requirements, and design is not fully constrained for any hold requirements. What is our challenge here is, in the earlier example, there was a clock. So it is very easy for us to apply a value, or you can create a base or a virtual clock, and we can check whether the frequency what we have applied, right? Whether the design has met that setup requirement as well as the hold requirements we verified. But what is the challenge in this particular design? Because it is a pure combinational logic block, which is an exceptional path. What is very important here is, how are we going to solve the problem without a clock? So what kind of constraints that need to be applied when it is a pure combinational design? That's what we are going to learn. Okay. So please remember what are the commands we have learned and how did we apply it. Okay. In the first example, we understood it is a counter design. So we created a clock and then we reported the clock and then we gave report time. But now here we cannot create the clock because it is a pure combinational design. Okay, let us solve the problem now. How are we going to do it one by one? Let us understand. We go to the tools and we can go to the timing analyzer right now. Here timing netlist. And now if you ask the tool that report clocks, you can see that it shows that there is no clock path to report. Because your code is not having any clock. It is a pure combinational design. How are we going to solve, or how are we going to perform timing analysis if the design is a purely combinatorial design? That's what is the kind of learning that is going to happen right now. What is the takeaway here is we are going to apply two commands. One is equivalent to the setup requirement, which is called as a set max delay. And the other one is called as a set minimum delay, which is equivalent to the hold requirements, because there is no setup and hold analysis here, because there is no flip-flop at all. But then we have to provide a maximum delay and we have to provide a minimum delay. That is what we are going to apply for this design, and we are going to perform timing analysis. So this is very critical and important for us to understand, because this provides us a good idea on how do we constrain a pure combinational logic path. Right. Where are those commands? How do we apply them? Let us understand that right now. In the Constraints tab, you can see we have seen create clock. But now what we wanted to try is called as the set maximum delay. And the other one is called as set minimum delay. These are the two things we are going to apply right now. The one is called as a set maximum delay, that is equivalent to the setup analysis I mentioned. And then the set minimum delay is just equivalent to the hold analysis. Even though there is no setup and hold here, we have to apply two specific commands for constraining a pure combinational logic path. First, let us try set maximum delay. It opens a dialog box. There are 2 points that need to be considered here. One, you can see there are 3 important things that need to be noted down. So one is called as from, to, and to. From, you can say which input, through which net it goes, if you are very much aware that we can provide it. To, then you can say which output put. Okay, so you can say from, through, to. Now, if you have everything, then it's really good. So we say from, we say through, we say to. Otherwise, we can say from to. Otherwise, we can say only hyphen from, then hyphen to. But the problem is when you say hyphen through, there are chances that it may take constraints for the wrong paths also. So it is always very critical and important that you should say the starting point hyphen from and hyphen to. It is mandatory. Even if you don't know through, but from to is important. Without that, if you constrain, there are chances that the timing analyzer will take wrong paths also to constrain it. Okay, the set max delay. What are the other 2 points which I mentioned to be considered? One, you can give the delay for all the inputs and all the outputs at the same time. Or we can specifically provide from this input to this output, you take this value. From this input to this output, you take another value. Like that we can provide. But the easiest logic is also provided in the timing analyzer tool, where we can specify from all the inputs to all the outputs, this is the value. Like that we can provide. Because in our case, it is only AB and some carry. There may be a path from A to S, there may be a path from A to carry, there may be a path from B to S, there may be a path from B to carry. In these paths, which is the longest path, that's what we are going to find out. For that, we need to provide some value. So I say here, from all inputs and say to all outputs. From all inputs to all outputs, I'm going to provide a value. What is the delay value? For example, I say 8 nanoseconds. I'm not very sure. This is just a random value, right? I don't know which is the critical path. Just understand how we are trying to debug here. When I say from all inputs to all outputs, when the delay value is 8 nanoseconds, let us assume, and I say run this, right? Let us see what it is taken by the tool. You can see set max delay hyphen from. all inputs to all outputs, I have given a delay value of 8 nanoseconds. Let us try the same with hold analysis. So let we select the minimum delay. And in the dialog box, you give here all inputs to all outputs. I say, for example, nanoseconds. Right? Let's say run. So this is given. Now let us see the time. We will check for the worst case analysis. You can see that. What we have provided is we gave 8 nanoseconds as the delay. But what is the data path delay is 8.006. The path is violated. Right? If you would have given 8.5, that path would have met timing. Right? We are not very sure, right? What is the data path? Now we are very sure that what is the data path. Now, which is the longest path here when you say A to S is the longest path? Right? It starts from A and ends at some. This is the longest path. What are the other possible paths you can see? A to carry, B to S, B to carry. A to S, A to carry, B to S, B to carry. When you say all these other paths are meeting timing, because their delay are lesser than 8, 7.803, 7.756, 7.59. Whereas this path is having a delay of 8.006. Requirement is 8 and arrival is 8.006. When you subtract this, you are getting a negative number. Okay. What kind of analysis we have to see here? First, we should analyze the path summary. Okay. And you should see here, there are no clocks defined in the design. We should keep that in mind. Okay, go to path summary. What is very important to note down here is on the launch clock, you can see not applicable. And in the latch clock, you can see not applicable. They are NA. That means they are not available. There is nothing to be considered there. And what is the requirement we gave is 8. And what is the arrival value? That means what is the time exactly it is taken is 8.006. The required time is 8 and the arrival time is 8.006. Therefore, the path is violated. And in the waveform, I wanted to see the detail. You can see that this is launch and this is your latch. It is not like a clock. Just to take a delay, that's all. Okay. Now, what is happening is we wanted at 8, but then it comes after that. Therefore, you have a violation. When we click statistics tab here, you can see that the data path delay is 8.006 and it shows number of logic levels 2. There are 2 logic levels. Okay, can we find out is it a 2 logic level path? When you say, we can right click this and say locate path and go to the locate in technology map view. So that you can see there is a 2 logic level path. You can see there is an input buffer and then it has to go through the combo logic and then it should reach the output. Now it has to cross these people to reach the output. Now there would be a delay involved for these buffers, and then you should also consider that what is the time taken to reach the S. This A to S is the longest path. Okay, let us see A to C. When you say, we can go to locate path and say locate in technology map viewer. You can see that this is the logic. You can see that. But this path is not having any issues because the data path delay is less. Okay. Now, what is our thought process is you were expecting that it can work at 8, that is your maximum delay, then it doesn't work. Okay, right. Can we modify this? When we say definitely we can modify. But before that, we should see what is happening on the minimum delay analysis. That is also very important for us to note down. Again, we can go back and double click report timing and select the hold and say report time. Now, if you see here, A to S, the data path delay, all are meeting timing. So when you say, if you go to the path summary, it is arrival time minus required. Required time is, we gave 3, right? It is AT minus RT, arrival time minus required time. So it is a positive number. If you go through the statistics, data path delay is 7.143 because you can see the interconnect, cell delay, all the informations. If you note down, this accounts to 7.143, and what we asked is 3. So it is a positive number. Therefore, the design is not having any hold violation. It is having only setup, and that too one path is failing. Okay, easiest way to solve this problem is what? When you say we will increase this 8, for example, 8 is not meeting, you can say it is 8.1 or 8.2. In a small design, it is easy for us to do like that, and then we can come back. That is not the case when the design becomes quite large, right? Because we cannot see each and every path and then change it, because you change in one, it will impact on the another path. But in our case, it may not have much impact because there are only 4 paths in the design. If I have 4 million paths in my design, and if I just change in one path, that will have impact on another path. Okay, that is very important. During our hands-on lab, we will have a case where there are 2 clocks, there is more than 1 clock in the design. And how are we going to constrain them? We are going to understand. So in that case, it will be very interesting for you, where that we try to impact on one that will provide a negative impact on the other. Okay, so those kind of considerations should also be taken into account. Okay, let us change the constraint again. So you go back to the set max delay again and say from all inputs, say to all outputs, and I say, for example, 8.2 nanoseconds and say run. Now let us run that once again. Now you can see that since we gave 8.2 and the delay was 8.006, it is meeting time. Okay, let us see the path right now. You can take this to the planner. And you can see that path which takes into account. So you can expand that here, which is the arrival path. And we can see which is the input and output. And what are the objects that need to be located? You can see that here, which provides the details of the number of logic elements, how many are available, and the informations are provided here. Similarly, we can also see the rest of the other things now. Resource property editor. You can see that editor. So this will close it and we can try that. All the information you could see. Right. So what are the important informations that need to be noted down? Is you can see right now, how do we constrain a pure combinational design? And then we have also seen how we can apply the clock for a specific logic. You wanted to save the results. Again, what we can do, go to the constraint, write STC file and open this and say, go to timing and a combo design. Go to the C drive and say timing and directly go to the combo design, open the STC file. You will have 2 commands here because earlier we gave a different value. We gave set max delay 8 nanoseconds. It didn't work out. We gave set max delay 8.2. The last one would be taken into account, right? And then set minimum delays. So there are multiple places, but then now we are able to fill. Now we know how to fill create clock. We also know how to apply set max delay and set minimum delay. One by one, we are going to learn how to apply false path, multi-cycle path, set input delay, set output delay, everything in detail in the afternoon class. But this will give you an idea of how to apply basic timing constraints, and also how those constraints can be saved into an STC file, and how can you view those STC file logic. Right, I'll just stop sharing, and then I will reshare the kind of presentation in which the combinational logics are taken into account. Let me show those 3 slides, and then let us consider that. Okay, now let us note down that how do you do a combinational interface. So in order to do a combinational interface, what we are supposed to do, use set max delay and set minimum delay commands. The set maximum delay and a set minimum delay commands, how do we apply? That's what I showed the demo first, and then I'm going to show you some 2-3 slides which explains the logic. So if you see the set max delay and set minimum delay, we can see from an input, the output you can see. I showed an adder example, like that any example we can take. So from this input to this output, you can specify a specific value, or else for all the inputs to all the outputs, we can provide a value. In our case, what we did is we can provide all inputs. Otherwise, we can also specify get underscore ports, and you can say D in A of 0, and then you can go to A B of 0. That means you can just say get underscore pins and say A. Then you can say get underscore ports, and then you can provide Y or carry, whatever you want. And then we can provide the value. So this will also work out. Otherwise, from all underscore inputs to all underscore output, that will also work. I showed you the basic syntax. Now you can provide all inputs and all outputs, but it is also possible to specifically specify the inputs and outputs. This is one more example where you can see set max delay hyphen from get ports in one out. Here you can see that in one, that is specifically input one only, but out star I have given. That means it can be either out one or out two. From this place to any output, I want to take 5.0 as the value. And from input to 2 to any output, 7.5. From input to 3 to any output, which is 9.0. Similarly, this is for the minimum. These are the different ways of constraining a pure combinational logic design. So what are the key takeaways now? Number one, we know how to apply or create or a base or a virtual clock for a design and see whether the design is having any setup or hold violations. We can analyze, we can debug, and we can also understand how do we validate the timing performance. Second, we know how we can constrain a pure combinational logic design. Right, let me stop here. And I request Bhaskar to continue the clock domain crossing session. And again, after lunch, I will continue with the timing exceptions topic.
Thank you, Padmanabhan, sir. So our next session is on clock domain crossing. It will be taken by Mr. Bhaskar Venugopal. Before that, we would like to share his brief profile with you. Mr. Bhaskar Venugopal is a system validation expert at Intel's Programmable Solution Group. Bhaskar holds dual degree in Masters of Technology in VLSI from Satyabama Institute of Science and Technology, Chennai, and Masters in Applied Electronics from Bharatiya University, Coimbatore. Bhaskar has about 15 plus years of experience in front-end design and has worked on design and development of a variety of IPs, subsystems, SoCs that caters to networking, high-speed computation, and AI solutions. Bhaskar has rich experience on ASIC and FPGA and has worked on debug architecture for next-gen, highly complex ASICs. Bhaskar is more passionate to teach and conduct classes in area of VLSI and associated emerging areas to college students and tech community. Bhaskar sir, welcome to this Joint Faculty Development Program. I made you the presenter. Now I am handing over the session out to you.
Thank you for your warm introduction. Am I audible?
Yes,
Yes,
Bhaskar,
Bhaskar sir.
you are audible.
Okay. A very warm welcome to all the participants here. Good morning, good afternoon. Let's get started this session. Do you see my screen?
Yes, Bhaskar, it's clearly visible. Yeah, you can go ahead.
Okay. Thank you, Paddy. Okay. Welcome to clock domain crossing session. In this session, we will discuss about what is how the complexity of designs have grown. How many clocks typically today we have in the designs that are available in the market, and why clock domain crossing is very crucial, and what all strategies one should consider while building a design or while implementing certain design. And potentially there are some best known methods to implement clock domain crossing techniques. We will be discussing about those things in this upcoming session. So multi-clock design. Say we have a design and that design takes inputs from some external world, takes that inputs, process that information, then sends it out back to the external world. The external world may give the information to the design with respect to some operating clock, some frequency. The internal logic may operate at some frequency. Again, the external consumer may be operating at some different frequency. So how do we coordinate all these clock frequencies? How do we establish a proper handshake method so that whatever valid data we got from the external user application logic, that is properly handed over to the design, so that the design process it correctly as per the functionality, then hands off the process results back to the external world. So today, if you see, you take any chip, any SoCs or any FPGAs which are available in the market, the complexity has grown drastically. They have millions of gates inside it, and any feature can be and they support custom features. You want to build a AI application, you have a solution for it. You want to build a networking protocol, yes, you have application, you have a solution for it. So the designs today have grown drastically in terms of complexity, and in order to meet those complexity, in order to increase the performance of the device, say for example in terms of processing capability, the frequency of the clock, the operating frequency, the design the frequency in which the design operates, those also have grown. So in this example, let's see what is mean by multi-clock design. So if you consider this particular block, where my cursor is moving, let's assume this is one particular design. This design is getting its inputs from someone else. So the inputs are these parts and the outputs are these parts. It may receive its inputs from the neighboring subsystem or the neighboring module, or it may directly receive its inputs from the external world also through the external interfaces. So now if we see, it takes the inputs and then the inputs feeds to submodule A. Let's assume this is one particular subsystem. Within subsystem, we have different submodules. So this external input feeds submodule A, submodule C, and submodule G. If you see here, these three modules are operating on clock 1 frequency. Then if you see here, from G, the information is passed to module H for further processing. This module is operating on clock 2 domain, clock 2 frequency. Then after A and C hands off after A and C has processed the input, they hands off the data to module B and D. If you see here, these modules operate on clock 3 frequency. Finally, from B, D, and from G, the inputs are, the processed outputs are handed over to these two modules, namely E and F, and from B directly it goes to output. These are all operating at clock 4 frequency. In this example, we see the inputs are coming from neighboring modules and it goes to, the outputs are going to another neighboring modules. But within this module, we are seeing 4 different clocks. So now if we consider the chip, complete chip, think of how many clocks it could have. Typically today we have close to 15 to 18 PLLs in a complex design, in a complex SoC, and lot of clock handshake happens between one module to another module. Basically, these are introduced to meet the custom requirements, especially to improve the throughput and the performance and to increase the compute processing. So now let us go a little bit deep into what is clock crossing and what is meant by synchronous and asynchronous clock crossing. Okay, synchronous crossing means, say you have a clock source which is from PLL. So we all are aware of what is PLL. Okay, a PLL is a device which generates a clock. You feed a known reference clock to it and you go configure it to give a specific output frequency. It will give you a frequency of desired configuration you have did. For example, it may take 25 megahertz clock from a crystal, and you can go configure this PLL to give one frequency which is of 200 megahertz, another frequency of 100 megahertz. Now, these PLLs are the source of clocks. In your, let us assume in your design we have one PLL called PLLA. You have another PLL which is called PLLB. This PLLB outputs generates one clock which is again a frequency of 100 megahertz, and that is called as H clock. Okay, now in we are seeing 200 megahertz clock, 100 megahertz clock coming from PLLA, and another 100 megahertz clock coming from PLLB. Though the frequency of these two are same, we cannot call them as synchronous, because they are originating from two different PLL sources. Okay, so synchronous. Okay, synchronous means we can call this. Okay, from PLLA we have one clock output which is 200 megahertz, another clock output which is 100 megahertz. I can say these two clocks are synchronous, though the frequency is different, but they are originating from the same source PLL. Basically, the root is same. Only thing is the frequency difference is 1:2. This guy is operating at this guy's frequency is 200 megahertz. This guy's frequency is 100 megahertz. So if you know the clock and phase relationship between two clocks, then it can be called as synchronous clock crossing. Okay, if you cannot determine the frequency and phase relationship, or if you know that these two clocks are originating from two different sources, then they are asynchronous. Though the frequency or phase relationship can match, but they are originating from two different PLLs, so they should be considered as asynchronous. Okay, so a synchronous clock crossing, a well-known frequency and phase relationship. Example is these two clocks, clock 200 and clock 100. These are synchronous to each other. They are originating from same PLL with a relationship of 1:2. With respect to this clock 100, this H clock 100, these two are asynchronous to each other. They are originating from two different PLLs. This is one basic thing which everyone should understand. To first understand what is the clock frequency relationship and where are the sources they are originating from. Then if you understand this, then most of your problems are solved. Okay, now why we should examine clock crossing? Like I mentioned previously in the block diagram which I have shown, today the inputs are coming from the module that gets inputs is on different clock domain, and it processes it on different clock domain and hands over the process data in another clock domain. So in this process, there should be a proper if we don't take care of proper handshake mechanism, then there could be potential issues. These potential issues might cause into silicon bugs. Okay, so what are the potential issues that could arise if we don't take care of this clock crossing? Okay, unsafe clock crossing leads to metastability. It also leads to data loss because of not proper handshake happening, and data incoherency. The sender might have sent data ABCD, but the receiver might have seen it CDBA. So some misinterpretation happened due to due to not having proper clock crossing structure in place. Okay, so any handshake happening between one module to another module operating on two different clock domains, that is called as clock domain crossing. And believe me, these issues could cause could cause serious damage to your design, and potentially it could cause your complete chip to fail in terms of functionality. Okay, and if it fails, it is very difficult to debug these issues in the chip, because we don't know under what corner case, what scenario, what kind of handshake is failing, and it is very hard to catch this, and it's time consuming process. Okay, so the best way is do a thorough check when you are building a design. Correct by construction. Okay, while you are designing a block, it should be correct. Okay, you should have a thorough understanding of clock relationship. Okay, so now let's try to understand what is clock domain crossing. Let us assume I have module A which has one flip-flop in it. Just an example. Okay, and I have another module which is called module B, which has another flip-flop in it. So now this module A, which is highlighted in blue color, okay, is operating on clock C1 domain. This module B, the flop which is in module B, which is highlighted in this, which is highlighted by this red box, is operating on C2 clock frequency. Now, unless I know what is the frequency relationship between this C1 and C2, I cannot say whether these two are synchronous or asynchronous. So now this is a typical example of clock domain crossing. Let us assume C1 is originating from one PLL and C2 is originating from another PLL. Then we can clearly say these two are asynchronous designs. That means this guy is operating on different frequency, which is C1. This guy is operating on different frequency, C2. Now, if this is a source, this is a destination, then a proper handshake mechanism should happen so that a data from C1 domain will be properly handed over to module B, which is operating on C2 domain. Okay, it is like you are establishing a kind of handshake mechanism when you are trying to interact with a person. Okay, say you are a person who know only English, and you are intent to talk to another person who knows only Japanese. Then you should have a kind of translator in between, a kind of mediator who can do a proper coordination of, and he can properly communicate what you are intent to conveying to the other person, and vice versa. Okay, so this is an example of clock domain crossing. Two designs operating on two different clock frequencies. These and the frequency and the clocks are originating from different PLL sources. Those are called as asynchronous designs, and this is a typical example of clock domain crossing. So now we said if we don't take care of this clock domain crossing, then it could lead into metastability. Now let us discuss what is metastability. Okay, let's say for example this A. Okay, let me go into a little bit basics. We all know from every flip-flop it has some set of physical characteristics. Basically, it has a property called as setup and hold time. Okay, setup time is the window where the data should come and should be stable before the arrival of clock edge. Similarly, hold time, the data should remain stable after the arrival of clock edge. That if these two properties are not taken care properly, then your design may lead into timing issues, like what Padmanabhan has explained in the previous session. It might, the design, you might not be able to converge timing. Your design may have some potential timing issues. If timing issues are not taken care, it might lead to functional failures. Okay, so in this example, let us assume this source flop, which is FA, is trying to convey information A to this destination flop FB. Now, if this FA, say with respect to C1 clock, this module has sampled the input and it has placed the data on the Q output of the flop. Now, with respect to the C2 clock domain, if the A output transitions very close to the rising edge of the C2 clock domain, then it might lead into metastability issue. That means the property of setup and hold is getting violated. If there is a violation, if that gets violated, then it is high likely that this flop may not sample the correct valid data. So let us see with respect to this waveform. Now, let's assume this is the C1 clock frequency and this is the C2 clock frequency. Okay. So with respect to this C1 clock here, if you see, it is the data is placed at the output of the flop, this flop where my cursor is exactly the point A. Okay. At the value at point A, when the clock is toggling from 0 to 1, this is called as rising edge. The clock is 0 here and it is rising here. So on this edge, on this point where my cursor is there, at that time, for example, if you see, the value of data is 0. Okay, but what happened with respect to C2 clock? This is the rising edge. So now C2 could not able to see a stable value. He sees the value slowly ramping up. He could not able to predict this particular state where exactly my cursor is, whether this is logic 0 or logic 1. I am confused. Okay. This is what is called as metastability problem. Okay, the output, since the Q output, which is nothing but the A, has not settled to a stable value at this point, the destination flop FB in this case, he could not able to sample a proper logic 0 or logic 1 because the voltage, because the signal is still not settled, it is still ramping. If the rising edge has occurred here somewhere, it would have sampled logic 1. If this rising edge have occurred somewhere here, it could have sampled 0. But now it is oscillating. It doesn't know what value to sample. So and this ramp for the, typically this is just shown in the diagram like how it is, but in real analog voltage, if you probe this signal in oscilloscope, you will see something like this. It may not be steep like this. It may not be a kind of slope like this. It may be a kind of oscillating signal because things are analog in nature. Okay, but the logic inside, based on the threshold voltage of the particular process, if the voltage level is above the threshold voltage, it will sample it as point logic 1. If it is below the threshold voltage, it will sample it as point logic 0. But there would be an intermediate state where the signal is oscillating. It has not settled to a known good value. So that phenomena is called as metastability. Okay, but this settlement might take some time. Let's say if you give one more clock cycle, it might have settled to either logic 0 or logic 1, but there is no guarantee that it will settle to a valid value, but it might settle to a legal good value. It could be 0 or good, it could be 1. So this is the metastability concept. And how it impacts, say you have transmitted logic 1 to the destination, but the destination has seen logic 0. Upon logic 1, you are expecting that this module will take some action. But since he has not seen logic 1, he has seen logic 0, he will not take action. Then you will be waiting for some response from this guy. Since no such response happened, you will hang, which is just an example use case. That means your system gets hang. If your system gets hang, which means your feature is not going to work correctly. So how can we reduce metastability? Now we understood what is metastability. Now, is there a way to avoid metastability? Certainly no. You cannot avoid metastability as long as you have multi-clocks in your design. But can we reduce metastability? Certainly, yes. We can reduce metastability. How? By using special structures. These special structures are called synchronizing elements, synchronizers. These are again digital circuits which will be placed between the source and the destination. These circuits are custom built and have certain characteristics. These helps to reduce the metastability. Okay, basically we use a two flip-flop synchronizer. People typically call this as multi-flop synchronizer. Basically, these synchronizer flops are clocked with respect to destination clock domain. Now let us take the same example. Your A started oscillating. D might have seen a metastable value, but the first flop of the D has seen a metastable value. In the second flop, it has seen a stable value. It could be 0 or 1. So having this flop might enter into metastability because we don't know, because the A has changed very close to C2. But when the C2 rising edge came, the B output was stable, and in the next clock, this flop could be able to, he could able to sample a valid 0 or 1. That means he has sampled a stable value. He has not seen a oscillating value. He has seen a stable value and he has sampled it correctly. So by using a two flop synchronizers, metastability can be reduced. Again, these two flip-flops are special cells. These are not like normal flip-flops. These are metastable hardened flops. Okay, to be more specific, these flip-flops have more gain. Basically, if I go back to this previous diagram, the destination flops, the synchronization flip-flops will help to will 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 help to make this ramp very faster. It will make it like this, so that the destination flop can see a value, a good stable value. It will avoid this slope, a slow ramp. It will avoid that. These are special cells which are custom built based on the process. And the person who is designing a logic, he should thoroughly understand what kind of synchronizer he has to place. Okay, you might have heard about the concept MTBF, mean time between failures. Okay, uh, so mean time between failure, it is a measure for a given toggling rate of your data and for a given clock frequency relationship, how long this structure will sustain, for how many years this circuit will work without any issues. Because any design you build, due to some aging factor of the components and due to the atmosphere where this design is implemented or deployed, the components might get impacted. So based on certain process, say for example, if you are building a design which is in 5 nanometer process, the process as a guideline, if your frequency is this, let's say for example, my C2 is 1 gigahertz, my C1 is 500 megahertz, for example, and the toggling ratio is too fast, then the process defines a guideline. Instead of two flip-flop, you can place one more flip-flop to increase the MTBF. So these are all some of the concepts which the designer should have in mind when he is implementing a clock domain structure in place. Okay, so this is one such common structure which is called as multi-flop synchronizer. Okay, basically it allows time for the oscillations to settle down. The first flip-flop takes time to settle down the oscillations so that the second flip-flop can see a good stable value and he can sample it correctly. Sorry. Okay. So let us see now. I want to transfer one bit of information from one module to another module. Okay, so let's see, for example, this is a module which is operating on clock 1, and this is the destination module which is operating on clock 2. Now for this 1 bit signal, if I implement this 2 flop synchronizer structure, it will work seamlessly provided multi-sampling is not an issue or missed sampling is not an issue. let me give an example. Let's say you have built a design which checks a parity error, which checks for certain parity. Say you have fed a 4-bit input and you are computing a even parity on that 4-bit input. The parity result you want to convey the parity result to the clock 2 domain. So if so, you will generate a parity and you will say, let's say the parity output has become 1, a logic 1. The result of parity is logic 1, logic 1. Now this one you want to communicate, you want to transfer to clock 2 domain. You don't care whether this one has been sampled by this destination either single time or multiple times. Internally, you will have a logic here which detects, okay, the sender has told me that the parity for the incoming data is 1. So upon receiving the data, I will do recalculate the parity. If I also see 1, then there is no corruption on the data. The interface is clean. So in that context, what time, whether the destination has sampled the parity bit a single time or it has sampled it multiple times, it doesn't make sense. It is still okay if he samples it multiple times. Similarly, do we have a constraint that you should sample it immediately that I sent in the next clock, in the immediate next clock cycle? No. As long as you convey that, hey, I have calculated parity and the parity value is 1, you also calculate parity and compare whether you are also getting 1 or not. So first time if he misses the sample, if he missed to sample it, then second time if he samples it, that is also good. So under these two assumptions, we can say we can use safely this structure to do a clock domain crossing. This is one example. So for example, this is with respect to clock. This is the clock 1 domain and this is the information which we want to transfer. If you see here, this is 1 cycle pulse. This info bit 1 is a 1 cycle pulse. You see, this is a clock. With respect to this clock, this information is 1 cycle pulse. Now, this is clock 2. So if you see clock 2 and the frequency relationship between clock 1 and clock 2, it is completely different. Now, this info bit 1 is fed to the first stage of synchronizer, which sees it here. Then it is sampled by the second flop in this next clock cycle. Here it is 1 cycle pulse, but here he has sampled it for 2 clock cycle pulse. It is still okay for the destination as long as the destination logic understands that you should treat this 2 cycle pulse into as a single 1 cycle pulse, or it doesn't care if whether this duration is for 1 clock cycle or 2 cycle. All he cares is only edge, then it is fine. So if let's say let us consider a scenario where you want to transfer a 1-bit signal which is originating from high frequency domain to a lower frequency domain. Let's say your source is operating at 500 megahertz and your destination is operating at 200 megahertz. So in that case, the 500 megahertz, you have to ensure that the signal that you are sending is seen properly by the destination. So if you know the phase relationship, you can stretch the signal for a certain duration that will ensure that your destination sees the signal. If you don't know the phase relationship, then you have to build a custom circuit where you stretch the pulse that has come from the source domain and ensure that pulse is stretched wide enough or long enough to the destination to see it. Okay, that is one of the technique which is used if you want to transfer a 1-bit signal from high frequency to low frequency domain. Okay, so the point here is signal must be stretched long enough so that destination samples it correctly. Okay, and you have to make sure that when the destination sees it, it should see it as a stable value. You cannot have any glitchy logic there. That will again cause metastability issue. Okay. Let us consider another scenario where you want to transfer a signal which is originating from low frequency to high frequency. In that case, if you don't if you don't have a requirement that my high frequency logic can sample the signal n number of times, then well good, you don't need to have any synchronizer. But if you really want to make sure that if the low frequency domain sends 1 cycle pulse, your high frequency domain also should see only 1 cycle pulse. Then you need to have a custom circuit where that custom circuit will detect a edge and it will generate a 1 cycle pulse for you. This could be for special scenarios, like say if this 1 cycle pulse, let's say you want to write a data into memory and that signal is a write enable signal, then the write enable signal should occur only once, 1 clock cycle in the destination domain. If it happens 2 clock cycles, then you are going to write the same data into 2 locations of memory, which is wrong. So if you have a scenario where sampling the same signal is not an issue, then you no need to have a synchronizer. But if you have a scenario where you have a strict requirement that if the sender is giving me 1 cycle pulse, receiver also should generate or see a 1 cycle pulse, then you need to build a custom circuit. Okay. Now, whatever we discussed is for a control signal, a 1-bit information. Typically, we deal with control bits also, but most of the time the data is more than 1 bit. Okay, you might be sending a 64-bit of data from one domain to another domain. Let's say you want to write a chunk of data to a memory. Then in that case, your memory, the data that you are writing into memory is not 1 bit. Your control signals of memory, the write enable, read enable, the memory enable, these are 1-bit control signals. But the data and address bus, these are bus information, more than 1 bit. Now, if I want to transfer a bus information from one domain to another domain, then will this 2 flops synchronizer work? Hello? Okay, let's continue. So let us consider we want to transfer a group of signals, which is called as bus. Bus means group of signals. Okay. Signals are grouped based on certain characteristics. Let's say, for example, address bus, which is, for example, a 16-bit address bus. In this example I have taken, you want to transfer a 32-bit data, for example. Now, if I use a double flop method, will it work? No, we cannot guarantee that it will work. Though the then in this case, you need to have the 2 flop structure added to every bit. You are increasing the complexity, you are increasing the gate count of the design, you are increasing the power of the design, and above all, this is not reliable. Why? Though the synchronizers are originating from same process, there is no guarantee that 2 synchronizers originating from same process will behave the same always. I will give a typical analogy. Let's consider we have twins. Can we say these 2 twins will always behave the same way? No, that is not possible, because each one have its own characteristics. One might be crying at the same time, another person might be laughing. Okay, so in this context, you cannot use, okay, it is not advisable to use dual flop synchronizers, the 2 flop synchronizers, to handshake a bus information that originating from one clock to another clock. Okay, then what else we have? We do have a structure in place that is called as mux based synchronizer. Okay, I will show you the diagram, then I will come back to the theory part. Okay, now let us consider this blue is our source. I want to transfer a address bus. In this case, let us consider this is address 0th bit, this is address 1st bit. Instead of 1, you consider this as 15. So 0 down to 15. Totally, I want to transfer 16-bit address from this domain to destination domain. Now, if you see the destination, which is highlighted in red, is operating in C2 clock domain, and the source, which is highlighted in blue, is operating in C1 domain. Now, instead of me synchronizing these individual address bits using a special synchronizer cells, what we do is from the source domain, we generate a kind of signal which is called as a qualifier signal, a kind of valid signal. It's like you are saying that I will mark my attendance. Okay, how do I know whether I came to college or not? By looking at the attendance. Okay, so that is a qualifier that says that, okay, this particular faculty had come to college today and he had took these classes. So similarly here, we should have a typical qualifier here. From the source domain, whoever is sending the address, he will generate an additional signal called as qualifier signal. In this case, we can consider this as an enable. Only when this enable is set, then only the signals on this bus are valid. Whenever the enable is not set, these signals are don't care. Now, instead of we synchronizing these individual address bits to the destination domain, what we do is we synchronize this enable signal to the destination domain, and the synchronized sample and the synchronized input is fed to the select input of this mux. Now, whenever the select input of mux is 1, the logic on the source will ensure that this address information is stable, so that this mux will propagate this blue, the address A0 and A1 signals to the destination flop, and the destination flop can sample them very safely. Now, when the signals are when the enable is set to 0, now the same signal is looped back here. Already it might have captured, so the address A0 to A15 are properly transferred to destination domain using this structure, which is nothing but a mux based synchronization scheme. The idea here is the source should keep the value stable. The source should generate a qualifier. That qualifier will be synchronized, and that synchronized qualifier signal will be used as a select input of the mux. So when the select input of the mux is enabled, then the signals are properly sampled by the destination flop correctly. This is a reliable structure. Now I go back to the theory part here. Mux based synchronizer. So the control, what you do is you take a control signal from source domain, synchronize it to the destination, and consume it. Okay. This way, all the data bits of a bus is transferred to destination domain reliably. This might ensure that your functional correctness also. Okay. Another method, typically what we have is a kind of handshake synchronization method. Now, this is one method, and we have another method that is called queues. Now, whatever we have seen is mux-based synchronizer, which is this diagram. Okay, this structure. Now, let's see what is handshake mechanism. Okay, now this is there is a two-way there is a concept called as handshake mechanism. It can be classified into two subgroups further, partial handshake or full handshake. It depends on really, it is implementation choice. You need to assess which scheme works best for you, whether you want to go for partial handshake or you want to go for full handshake. Let's take a look at it. Let's say, for example, this block, which is encircled in the dotted the blocks within this dotted circle, this is a destination domain which is operating on clock B. The signals which are towards the left side, these are source signals which is operating on clock A. In this method, what we typically do is we send a signal from A saying that first we send a kind of a notification to destination saying that I am going to send you new data, you be prepared. Then whenever the destination sees that new data, he will sample the data. Once the destination samples the data, then he will send it back to the source saying that I have sampled your data. Now you can place a new data on the bus. So this is the kind of handshake mechanism. It is like I am telling the receiver that, hey, I am going to give you new input, new information, you be ready. Then I place a new information on the bus. I will not change this content until I get an acknowledge back from the receiver saying that he has sampled it correctly. The receiver is, the flow is like this. I will place a data on the bus, send a notification, then the B sees it, he samples it, then he sends me a notification back. I consume that notification, then I go change the data. Then I am allowed to, then only I am allowed to change the new data. It means place a new data. Now, what is the biggest drawback in this scheme? The latency. User has to send the information, then wait for the B to give a ACK. Overall, if you see, this might take 7 clock cycles, typically with respect to this example. So today, to meet our end customer demands, how fast you process the data, that is one of the unique selling point. If you are building a design, the unique selling point is how many operations you can do in a given clock period, or how fast you are processing the data and throwing the output to the outside world. That is one of the unique factor. In that context, latency, if I say my design is going to take n number of clock cycles as a latency, then this design does not have any unique selling point. So this is a typical biggest drawback, the latency. The latency associated with this is with this kind of handshake is very large, and this kind of schemes cannot be afforded in today's complex designs where certain features are very crucial for our end customers. Okay, but I'm not saying that this structure cannot be used. This structure can be used where latency is not a concern. You say, okay, I place a data, I will wait for 5 clock cycles, then I will change the data. I'm still okay with this, with that kind of latency trade-off. Then you can use this kind of structure in place. So another approach, which is Q, a kind of first in, first out, that we call as FIFO, F-I-F-O, first in, first out. Here it is like a container where the source will put a data into it, then the destination will come and consume it. The source and destination both operate at 2 different clock frequencies, but there also there is some kind of handshake mechanism happens. So what are FIFOs? They are typically a storage element surrounded by a control logic. The logic that controls the writing part of the queue is called as write controller. Similarly, the logic that controls the reading part of the queue is called as read controller. Okay. So the concept here is you load the data into the queue with respect to clock domain A, and you unload the data from the queue with respect to clock B. Consider this as a container where you loaded the data, you loaded some stuff into the container, then you ask the other side logic, which is destination, to consume the data from the container. Within this container, you have some kind of handshake mechanism circuit inbuilt. This is one of the widely used structure today to do any kind of clock domain crossing, and this structure works very well for any kind of phase relationship or any kind of clock frequency relationship. The queue status is tracked using some special control signals. Let us look into it. Okay, so you can consider this block. This block is a queue, first in, first out, FIFO. Okay, what it has internally, it has a storage, a kind of memory, a buffer. Typically, we use dual port asynchronous RAM, which means the port A can operate on one frequency and port B can operate on another clock frequency. Okay, and we will build a small glue logic surrounding it, which controls the write part of the queue and read part of the queue. The write, here it is like this is the data that you want to put into the queue, you want to write into the queue, and this is the write enable signal. From this logic, you are getting a notification that how many more entries are available for you to push some more data. That control signal is called full. Basically, you need to have a notification saying that whether you can put the data or not. If you keep on putting, then you don't know whether your data has really gone in, whether it is really consumed, what it is. So this is on the right side. Similarly, on the read side, you want to read out the data. So you will get the data from this FIFO. This is a read enable signal. And you should know whether there is a valid data in the memory or not, so that you can go read it. If there is no valid data, then you will keep on reading the empty data. So you should have a kind of empty flag notification. for the receiver to know when he should initiate a read. Similarly, for the source to know when he should stop putting the data into the FIFO. This saves the latency problems, and this is one of the robust mechanism extensively used today in our complex SOCs. Any chip you build, people typically use asynchronous FIFOs. Okay. Now let us see a little bit how it works. So let us consider the FIFO is 4 deep. This is consider this as a memory element which has 4 depth structure. Now to address this 4 bits, I need 2-bit address input. 00 means this location, 01 means location 1, 10 means location 2, 11 means location 3. Now since I might need only 2 bits to address this memory location, but we will have one more bit. The pointers will have 3 bits. Let me explain you how it operates. Okay, but here we have considered the pointers to be 3 bits. Okay, bit 0 down to 2. Now let's consider on the right side, this portion is write, this side is read. Now let's consider the right side has placed a first data into location 0. Read has come and read back the data. Now in the second clock cycle, write has placed another data which is in entry 2. He has placed another data which is in entry 1, the previous data, then entry 2, the next data. Now the read has come and he has read first data, the data in the entry 1. Then he has read the data in entry 2. Now do we have any data in the FIFO? No, because we have read. So now the empty flag will get set. What is the condition to set the empty flag? Whenever the read pointer is equal to the write pointer, this indicates that whatever the data the write domain has placed into the memory, the same set of data have been read by the read domain. Now this is an empty condition. So now the empty flag will get set. So the condition to set the empty flag is the empty pointer should be equal to the write pointer. Write is put, empty is read is get. Now let's consider another scenario. Now a write has come and he has placed new data in entry 3. Now is the FIFO empty? No, because the get pointer is not equal to put pointer. So basically if this is pointing here and this guy is pointing here, so the FIFO is not empty. So the empty flag will not get set now. Now let us consider the same scenario. So we had one data in here. Then now the data has been read by the read domain. Now both the pointers are equal. Now again the empty flag will get set to indicate that the contents of the data are read out. Now let's consider another scenario. Now this guy has rolled back to pointing to memory entry 0, location 0. So the first word, the new first word is written into entry 0. Then second word written into entry 1. Then the next word written into entry 2. Then the next word written into entry 3. Now is the FIFO really empty? No, because the read has not read the last 4 new words that the write domain had placed. But in this context, can we say, since both the pointers are same, can we say that FIFO is empty? No, we cannot say it because this is a wrong. So now if you see here, if I blindly compare the write pointer with the read pointer to check for empty, it will give me wrong. It will give me a wrong notification. Now, since the pointer has wrapped around, in the first case, when the pointer has wrapped around, it might have the second bit, in this case, the MSB bit, the second bit might have become 1. So it is now pointing to location like 100, 101, 110, 111. Whereas in this case, this guy would be pointing to 011. So the MSB, though the LSB 2 bits are same, but the MSB bit is different. Ideally, this is a FIFO full condition because the write has wrote all the data into all three entries. Now, if he tries to write another new word, it will overflow. That means he is going to overwrite the old data which he has written into entry 0. Now, this is the exact condition of full. Now, let's see here. Full condition is determined by the write pointer and the read pointers. The LSB 2 bits should be same, and the MSB 2 bits, the MSB bit should be different. If this condition is satisfied, then the full flag is asserted. This is a condition to say the FIFO is full. So now you can understand why we took the extra 1 bit. Though my memory is 4-bit deep, though my memory has only 4 locations, to address 4 locations, 2 bits is sufficient. But we have took 1 extra bit. That 1 extra bit is called as a wraparound bit, which is used to determine whether the FIFO is full or empty. Now let's consider this read has gone read entry 0, entry 1, entry 2, entry 3. Now what will be the value of this 2 down to 0? It is 1, 1, 1. On the put side also it is 1, 1, 1. So if all the 3 bits of write and read pointers are same, then it is empty condition. So by having 1 extra bit, we can exactly determine whether the FIFO is really empty or full. Okay. So this is how typically a FIFO operates. So the concept is we take n bits to address the memory location and n plus 1, which is used as a wrapper bit to determine whether the FIFO is full or empty. The extra upper bit is used to determine pointer wrapping. If the pointer has wrapped and the remaining bits of the pointers are same, that means it is full. If the including the wrapper bit, if the pointer bits are same, that is empty condition. This is typically a concept how the FIFOs work. So to give a kind of complete flow, let's say this is clock domain A. The sender wants to place a data, so he will place the data here, load A. So if you see here, he has placed the data here. Then that data, which is nothing but okay, internally we can this basically shows us how the synchronization happens inside the FIFO. Now this address pointer is gray encoded. It is not a binary address, it is a gray encoded address. Now this gray encoded address is passed to this logic A domain, which is originating from the logic A domain. This gray encoded pointer is transferred to logic B domain, the clock domain, the logic which operates on B. Okay, he will synchronize it, and then the synchronized value he will compare it with this value for empty, because the empty flag is set, or okay, because the empty flag is computed on read domain. Okay, so once the synchronized pointer value is seen by the B domain, he will compare that address with his own address. If both the address are same, he will say it is empty. Okay, now if you see here, the pointer value, this pointer value has been compared against this pointer. Then now similarly from the B address, after converting into gray encoded value, it will be transferred to source domain to compare for full condition. So this is how the typical flow is. You convert the address into gray encoding scheme and transfer it to destination domain B. Thus the synchronized gray encoded value is used to compare against the B address to check for empty. Similarly, the B address converted into gray encoded is transferred to A domain, and A domain synchronizes it and compares it for full, because full condition is determined in source domain. So this is how the typical control circuit, the handshake circuit inside it, inside the FIFO. Okay. Now I told we have used gray, and we typically use gray encoding mechanism instead of binary encode. Why? Let's consider, for example, my FIFO is 4 deep. Okay. So to address 4 deep location, these 2 bits are sufficient to me, bits C and D. So 0, 0, 0, 1, 1, 0, 1, 1. This is sufficient to me. Now let us consider I wrote data into first location, then I wrote data into second location. Now this second location, this value 0, 1 should be transferred to B domain so that B can compare against his value to check whether it is empty or full. Okay. Now while transferring, what if this guy has become, ideally the valid value that I transferred to B is 0, 1. But what if B sees that as 1, 0 or 1, 1 or any other value? That means he is going to compare against a non-valid value, which could potentially cause functional failure. To avoid that, what we use gray code. Gray code, the property is only 1 bit changes at a time. Now, let us assume I have gray encoded the pointers. Now, I am transferring this value 0, 1 to the destination domain. Even if what could go wrong, the property, according to the property of gray code, only 1 bit can change. Okay, even if the other bit gets slipped, what could go wrong is he might see a new value or a older valid value. This potentially avoids the functional sampling a wrong value, thus avoiding a functional failures. So this is the reason why gray encoded the FIFO pointers, especially the address of the memory, are gray encoded before we calculate whether the FIFO is full or empty, before we determine a condition whether the FIFO is empty or full. Okay. So this is the property. So when crossing, only one value, whether it's old or new value. So if it is old value, it is still safe. You are not taking any action. If it is a new value, you are going to sample a new data. Okay. So now let's consider synchronous clock crossing. So that's how the FIFO mechanism works, and that's how and that's the importance of gray code. Why gray code based scheme is used to calculate the to have a kind of handshake over the pointers across clock domains. Now let's consider what is synchronous clock crossing, and do I really need a FIFO when I am doing synchronous clock crossing? Okay, so this is a FIFO, the queue, what we have discussed previously. This is my data, and this is my clock, and the write enable signal. Now, if a write and read clocks are synchronous, that means if they are originating from same PLL source, and if they are of same frequency, then we don't need a FIFO. Okay, so let's see what it is. If data can be read as soon as it's available, then a FIFO is not required. You might have just have a one single register, or even just a kind of direct handshake, a kind of using a kind of valid enable. Okay, but if you have a scenario where the read may not come and take the data immediately, but he will come and read the data at certain intervals, then you need to have some kind of storage mechanism based on the intervals. So you need to calculate, though it is synchronous, you need to calculate how frequent the write side is going to place the data, how frequent the read side is going to come and consume the data. What is this interval? According to that interval, you should calculate the depth of this FIFO. So FIFO is required to store the data temporarily until it is read. So you need to do a calculation to determine the depth of this FIFO. Okay. If consider this scenario, if the data comes continuously from the right side, then you cannot read continuously. Then you need to have then you cannot build a infinite depth FIFO. That means you will blow up the area of your design. The gate count is going to increase, and this is not a feasible solution also. So you need to have some kind of mechanism to stop the incoming traffic. Some way you should tell the other person who is giving you the data, saying that, hey, I don't have enough buffer with me. Please hold on your data. Let me notify you when I have some empty space so that I can consume your words. Okay. So kind of recap. Synchronous and asynchronous clock crossing. A person who is designing the block, you should have a thorough understanding of what is meant by asynchronous, what is synchronous, and especially what is the clock relationship, the clocks that he is handling. You should have a thorough understanding. If that understanding is very much clear, then you can sort out most of your problems. You should have then you can implement a proper structure in place. Once you have proper structure in place, then you can check whether the structure that you have placed is working as you expect it to work. If it is a 1-bit control signal which you want to transfer from one module to another module, you need to check, okay, this signal, the destination, how I want the destination to see this signal. Should I want the destination to sample it only once, or even I am okay if he samples it multiple times, or even if he misses the first sample, I'm okay if he samples at the 5th clock cycle, then you can go ahead for 2-flop synchronizer. Okay, even though metastability cannot be avoided, but it can be reduced by using proper structures in place. Okay, if it is a 1-bit control signal, yes, a 2-flop synchronizer, a double flop method, it works. Okay, but don't take it for granted. Think, do an assessment, and then have a proper structure in place. Because if things go wrong, it is very hard to debug these issues in silicon, in the chip. Okay, if your information is a wide address bus, a wide bus, think which scheme. We have 3 different schemes. Okay, these are robust schemes used across industry. Think which scheme works best for you based on your feature or functionality requirements. Okay, you can go ahead for mux based synchronizer, you can go ahead for a partial or full handshake mechanism, which is nothing but a kind of request act protocol, or a generic FIFO. Okay. So these are some of the techniques, and these are some of the techniques which typically we follow under industry-wide solution to do clock domain crossing of signals from one domain to another domain. Okay, but there are certain pessimistic conditions which you need to derive. Okay, if you want to say the FIFO is full, then you should communicate this information upfront so that the person who is sending the data, he should see it so that he should get ready to stop the traffic. It's like you are driving on a road and you are seeing for a red light. Here itself you are slowing down. You are not going very close to signal and putting a harsh brake. So it takes time. If the logic should have some pessimistic entries. If you know that if I say full now, it will take 3 clock cycles for the destination to see, for the original source to see it, then you should have at least 3 buffers, 3 locations available, so that whatever data which is on flight, which is already on the path, you cannot drop it, you have to consume it. So some more thinking is required, that we call it as kind of pessimistic full, pessimistic empty. Okay, I am saying that I am about to be empty. I'm not telling you that I am completely empty. I am about to empty in another n clock cycles. You be prepared. I can consume only 6 more words from you, like that. Okay. One big point, think before you decide which method to use. Okay, consider your design, consider your metrics. What is the key goal of this design? If it is high throughput and you cannot afford for any latency issues, then go for Q. If you think that this is only a control bit signal, then think whether you want to really go for 2-flop or 3-flop based upon the aging factors also. So yeah, with this we are done with our clock domain crossing session. Padmanavan, can you please take over?
Yeah. Thank you so much, Bhaskar. There are no questions in the chat, or we can provide the summary in the afternoon after my session. So it's
okay. Fine. Shall I stop presenting?
Yes, please. Yes, please.
Okay.
Thank you so much. Thank you so much, Bhaskar.
Yeah. Thank you. Thank you to all the participants for patiently listening to me. Have a good day. Thank you.
Thank you, Bhaskar sir, and thank you, Padmanabham sir. So now we can go for a break, and we will again rejoin at 1:30 p.m.
All right, we will do that. Yes.
Yes, sir.
Participants will again join by 1:30. Thank you.
Dear participants, we have shared the attendance in the classroom. You can check in the classroom drive. In case of any queries, you can raise your queries in the email ID, which is already provided in the announcement page. Thank you, everyone.